think all of you know, my name's Alistair Nolan. I'm a senior policy analyst with the OECD's Directorate for Science, Technology and Innovation. Thank you for all joining this final day of the OECD workshop on AI and the productivity of science, especially those of you who are coming in from far-flung time zones, from Japan through to the West Coast of the United States and Canada. A number of you have participated in addition in earlier days of the workshop, so welcome back. Now, we've addressed a fairly comprehensive set of issues in what the workshop has covered so far. And so today's focus will be on the future, what AI can achieve in science in the next 10 years. Just to note that the session runs from now, this is 2 o'clock Paris time, for 3 hours through to just after 5 o'clock Paris time, 1700 hours. At the end of the afternoon, I will say a few words about how all of this work is going to be used and put before OECD policymakers. So with that, let me welcome and thank our moderator for this session. That's Jeremy Frey, who's a professor of physical chemistry and the head of the computational systems chemistry, and at PIAA for AI for Scientific Discovery Network. So thank you indeed.
Thank you and welcome. It's a great pleasure to be the moderator for this session. I've listened to and taken part in some of the other sessions, and it's certainly been very exciting. And I'm sure you're going to draw a lot of interesting conclusions through this session and the reports that will presumably follow from this to the OECD's partners. Just a few housekeeping things to say. Obviously, we would like to encourage everybody to participate as fully and actively as possible. The talks will be for 15 minutes with 5 minutes question and answers after each one, and then an hour's roundup discussion at the end. So please get ready to ask questions. Put something in the chat, in the Q&A, the chat if you want, and we may keep those back till later. But please, actively participate. Let the speakers have their 15 minutes, and then we'll have the questions and then the questions at the end. So keep your cameras on if you can, just so that there's at least some people for the speakers to look at. It's useful, and not just me. But I appreciate that it's not always appropriate. But please keep the microphones off. I'm actually, the background is real here. I'm in my office for the first time in a while. I'm teaching after this session today. And so I apologize if when I'm talking that there's building noise coming through. Usually the microphones on the computer are fairly immune to it, but we'll see. Yes, when you want to ask a question, as I said, put it in the chat or raise your hand, and we'll try and make sure. Most of you show on the screens here, and in the chat thing I can see who's put their hands up. So I think that's all that we need to say at this stage. So welcome you to the afternoon. Listen, participate, ask lots of questions, ask particularly difficult questions of our excellent speakers here. Challenge them to things that will be really important. I think that's all generally. Alistair, is there anything else I should have mentioned?
No, that's great. Okay,
in which case, our first speaker today is, if I've got this right, it's going to be Ross King, talking on behalf of both Ross and Hector. And Ross, I think, is taking full advantage of the virtual working environment that we're often in, because I think Ross belongs to, still, I think, connected with Manchester one way or another, with Chalmers, with Cambridge, with
Manchester.
Turing. Not Manchester anymore? You say goodbye to them.
Yes.
Now, I'm not sure their web pages still say that. That's,
okay.
But definitely Chalmers and Cambridge and Turing, and present at a lot of exciting conferences, some of which we've arranged and had the pleasure of listening to Ross before. So today, Ross is going to talk, I think, on what is one of your favorite topics, really, that you were one of the first to start actually publishing on and asking people to think about, AI and the future of science. Ross.
Okay, thank you. Let me try and share my screen.
Yeah, that looks good.
Okay, I want to thanks Jeremy, and thanks to the Alistair and the rest of the OECD team for what's been 5 days of interesting discussion. been particularly interesting for me to this sort of meeting of communities. So it's like, it's not just AI and physical scientists, biologists, but also social science economists, which is quite a different community to meet and very interesting for me. So AI and the future of science. To me, I think it's clear that the future wealth, safety of society depends on better science and technology. I think if the world countries got together and cooperated, we have good enough existing science and technology to give everyone on the planet a good standard of living and healthcare and things like that. But I have little confidence that the world's nations will get together and share science and technology and resources. When I look around, I think, for instance, the climate change, if it's up to the politicians to save us from that, then I think we're doomed. My personal feeling is there. You know, I'm looking at what's happening in Glasgow, and it's pretty disappointing. I think the only hope is better energy efficient technology and better crops. So I think science is, better science is needed for the planet. And I think AI has a possibility, maybe the hope of making science and technology more efficient. The traditional name for application of AI to science is called scientific discovery, and it's nothing new. One of the advantages of applying AI to science is that I think we have in science, I think there's a clear philosophical understanding of what science is. I think the goal of science is clear, is to learn models that enable us to predict what happens in the real world. In machine learning terms, there's a clear, what we call objective function. You know, it's how well our models predict what happens in experiments. I believe the methodology of science is clear. Some philosophers of science would dispute that, but I think it's clear and can be mechanized. And I think it's interesting to compare and contrast making a mechanized science compared to, say, mathematics or art, where I think it's very less clear what's going on in mathematics or arts, and what the objective function there is far less clear, I think. And as I've argued before, that AI systems already have superhuman scientific powers. They can flawlessly remember vast numbers of facts. They can do flawless logical reasoning, unlike human beings. They can do near optimal probabilistic reasoning on small amounts of data, unlike human beings. They can learn from vastly more amounts of data than human beings can do. They can extract information from millions of scientific papers. Human beings can't do that. They can't read scientific papers, but they can extract information from them, etc. So these superhuman powers are complementary to what human scientists have. And AI is a well-suited task science is a well-suited task for AI. Its scientific problems are abstract, like the games of chess and Go, which AI systems have triumphed over humans. But it involves the real world, which makes it far more important than these toy problems. And scientific problems are restricted in scope. To quote Lewis Carroll, there's no need to know about cabbages and kings and many things. If you have AI systems working on a particular scientific problem, it doesn't need to know about vegetables or politics. It just needs to know about that particular area of science. So that restriction of scope really helps to make it possible for an AI system to work. Another big advantage is that nature is honest. By this, I mean that if a human or a robot does a scientific experiment, we're pretty confident the real world's not trying to fool us about how the system works. And that's quite different if you compare to having an AI system in an economic game or a military game or something like that, where the agents are dishonest. It makes it much easier for the AI system to analyze what's happening because nature is honest. And also strongly argue that nature is a worthy object of our study. So many of the smartest people in the world are working on AI, but what they're doing, most of them, is developing more addictive advertising for large corporations. And the world's faced with all these problems. We have pandemics, food insecurity, climate change, and these smart people are developing AI tools to just make better advertising. I think it's a tragedy, personally. And I would argue that the generation of scientific knowledge is a public good, at least if that knowledge is in the public domain. So there's a long history of applying AI to science. It goes back to the 1960s and 70s with Joshua Lederberg as Project Metadendral. Interestingly, he won the Nobel Prize for Medicine, but he started this project. He taught himself to program. He was very interested in AI. He was interested in formalizing science using logic. Also involved was Ed Feigenbaum. He got the Turing Award for his work on expert system. And Carl Djerassi was the main chemist, and he really should have got the Nobel Prize for his work on birth control pills, I think. And the point of Metadendral was part of the Viking probes to Mars. They sent a small mass spec machine to Mars looking for life. And the idea was that because Mars is so far away, we need an automated system to do the science there. And unfortunately, at the time, the computer science computers weren't up to doing this. But it was a fascinating and very influential project within AI. So Metadendral was actually one of the first ever machine learning programs. Another highlight in AI scientific discovery is Bacon. The main person there was Herbert Simon, is the only person to have won a Nobel Prize and a Turing Award. And controversially, it claimed to have rediscovered a lot of scientific laws like Kepler's laws of planetary motion. It's controversial because they sort of cleaned up the data, and an AI system had basically just needed to find quite simple patterns in quite clean data, quite different from what Kepler actually had to do in reality. But nevertheless, it was an important project. So the current state of the art, I would say, is closed-loop automation in science, this idea of our robot scientist. And there you're trying to build an AI robotic system which can do simple forms of scientific research autonomously. So such a system has background knowledge about an area of science. That background knowledge represented in logic and probability theory. And these are the best ways we know how to represent knowledge. It has a way of autonomously forming new hypotheses about the area of science. It can also autonomously decide on efficient experiments to test these hypotheses. It can then program a laboratory automation, a robot, to physically execute the experiments, look at the results of these experiments, analyze them, and change the probabilities of its hypotheses based on the experimental observations. And it can then repeat that cycle until some resources run out, or there's only one consistent theory with the background knowledge and experimental evidence. So that's the basic idea of a robot scientist. And the motivation for doing this, one motivation is technological. We want to make science more efficient. And such systems can work cheaper, faster, more accurately and longer than human beings. They can work 24/7. They can also be more easily multiplied than human beings. It doesn't take 20 years to grow a new one. If we have successful robot scientists, we can build thousands of them quickly. And I'd also argue that the science produced by such automated systems is better in quality than often done by human beings. And that's because they record things in much greater detail, much more semantic detail than normal human being scientists do. Because we're only human and a bit lazy, to record things. So the quality is potentially better, which makes it more easy to replicate the results. And one thing that's come to the fore recently is that they're more robust to pandemics. We saw Andy Cooper's robots in Liverpool running around in the dark during the pandemic on BBC TV. It's quite impressive. There's a lot of different systems now appearing. Material science is one of the most commonly applied areas. There, for instance, the Air Force in the US have a system called Ares. I visited Samsung Labs, who have spending a lot of money on automation. Another big application area is drug design. Many big pharma companies are doing closed-loop automation in their drug design. IBM have a lab in Zurich doing this. We had IBM speaking at the meeting. There's a company in the US, a unicorn called Recursion, which based its whole business model around this. Another area is protein design. There's a startup in London which is doing a lot of this called Lab Genius, etc. So that's the past and the present. What's the future going to be? Since I'm talking, I have the privilege of talking about my own work, and I'm fascinated by biology. Biological systems are incredibly complicated. Even the model biological systems like E. coli and yeast have thousands of interacting components. Thousands of proteins, genes, small molecules, all interacting in complicated temporal spatial ways. And they do quite weird things because they evolved over time, rather than this idea of that the simplest explanation is most likely one doesn't work particularly well in biology because of their evolutionary history. And I would argue that there's not enough PhDs in the world to disentangle these systems anytime soon. And on top of that, as one of the people here today, Hiroaki Kitano, has pointed out many times that these models are beyond the human intuitive understanding. We need help from AI systems. And I'm building this system called Genesis. It's unlike most new scientific instruments, which are normally designed to make some better form of observation, like a bigger telescope, more powerful synchrotron, etc. The idea of Genesis is to basically industrialize an existing form of experiment, an instrument, which is called the chemostat. So Genesis will have, most labs have maybe 10 chemostats, and Genesis will put together 10,000 little micro chemostats, and each one will be able to have a separate experiment designed by the AX system every day, and be able to take readouts of these systems using mass spec machine and transcriptomic experiments, measurements using sequencing. And because there'll be 10,000 planned experiments a day, we need an AI system capable of designing and planning that. No human being could ever plan so much work. Here's a little picture of Genesis, the complicated micro chemostats. And I wanted to finish by sort of not just a 10-year perspective, but the next 30 years, this thing called the Grand Nobel Turing Challenge, which I'm involved with. And the idea is to build by the year 2050, develop an AI system that can make major scientific discoveries worthy of the Nobel Prize. And Hiroaki Kitano has been one of the main people behind this. He originated the idea, myself and Yolanda Gill, who was president of the AAAI. We had a meeting in London just before COVID restrictions. It was a very successful meeting where we started to plan out a road plan to what would be needed to build an AI system capable of winning a Nobel Prize. And there is this continuum of arguments. So in chess and Go, there is this continuum of ability from novices to grandmasters, and AI systems have followed that path over time. So that the first AI systems in chess were very poor. Now my mobile phone can easily beat the world champion. Similarly, AI systems followed this path in the game of Go, and I think there's an argument that they may do so in science. So an argument in science that there's also this continuum of ability from the simple forms of science which existing autonomous systems can do, up through the types of science that you and I can do, up to the grandmasters of science. And if you buy this argument, then it's likely that AI systems get better and better at science with the improvement of hardware, software, more data. And 10 years ago, actually, the physics Nobel Prize winner Frank Wilczewicz said that in 100 years' time, the best physicist will be a machine. So there's a technical challenge, what needs to be done to achieve this. Such a system will need to be able to make a strategic choice about its research goals. No machine can do that. It would need to be able to form exciting and novel hypotheses. Most systems at the moment can only form hypotheses within a restricted area. It would need to be able to design protocols and experiment to test the hypotheses. No system is able to do that at the moment. They can only test the hypotheses using pre-cooked types of experiment. They'd be able to needed to notice and characterize a significant discovery in terms that people would be able to comprehend. They need to be able to communicate that in a form of communications to other scientists. No system at the moment can do that. It needs to be able to persuade people what it had found is important. That's also something which no system can do. It's interesting to look at the past.
Just be on the end of your time, Ross, but I guess
yeah, I'm just almost finishing. A couple of slides. I suppose the biggest question for me is actually, would we need to solve general AI to build a system to do science, which is of Nobel Prize quality? We didn't need to do it for a Grandmaster chess or Go, but maybe science is different. Hector and I have been working on a roadmap, which you probably can't see the slides particularly well, but we have starting to develop sort of steps on the way to achieve this. And to conclude, I think there is this vision that human and AI systems can work together to do better science, neither can alone. And I think it's interesting to realize that human computer teams still, at least until very recently, played better chess than machines alone. So humans and computers working together can do better than either alone, even in areas where humans or computers dominate. And this will, I think, hope to improve the productivity of science and benefit society. Okay, and so thank you for your attention. And thank you, everyone.
Thank you very much, Ross. Really good at setting the scene. So I invite some questions. There's always the problem of knowing whose hands up first. I think it was probably Sašo may have just got there first, or maybe it was Bart. Let's start with Sašo and then Bart and then Anthony.
Thank you. I'll be quick. Ross, what is your opinion on the ability to actually formulate existing scientific knowledge in the form usable by robot scientists? Because scientists really need to take advantage of existing knowledge to get further, and getting this knowledge to the robots I see as a major obstacle.
Yes, so representations here, this is, we try to, representing knowledge is a key part of all this, and it's, the systems, they don't have scientific knowledge. It'd also be very good if they understood some basic, knowledge which human beings have about the world, which they don't have either. So I think that's a key part of it all, yes, how to represent knowledge.
I think, Eirini, actually, you were there before the others, and you've just disappeared again with the hands up.
Can I go?
Yes, please.
Sorry. Yeah, so I had a question about serendipity and the nature of discovery. So obviously, science has a lot of happy accidents that could take the form of discovering something you weren't looking for, or solving a different problem than you expected, or doing lots of unfocused work that leads to an epiphany or a kind of whole new white space in science. So what are your thoughts on that question?
Yes, well, I think there's two parts to that. Having accidents, machines have accidents. My robots drop things quite frequently and things like that. So the difficult part's not so much having the accidents, it's recognizing when you see something important. Famously, Fleming and spotting that penicillin was killing the bacteria and things. I think it's an important question, and there's a lot of work actually in AI trying to recognize unusual things when you see it. One of the problems actually, in my scientific career, I once noticed something I thought was quite important accidentally. It's caused by the postdoc not realizing what an enzyme should be. But I could never persuade any scientist that was important. And eventually other scientists found it and published it in Nature, but I couldn't persuade anyone about it. So it's not just about having the accident, it's also about persuading people and having the ability to do the further experiments, which I couldn't do. So I was in a computer science department at the time and wasn't really access to the facilities to test it properly.
I think that's a very good point. Bart.
Yeah, no, very, very, very good talk. Yeah, my question is more, in the beginning you mentioned sort of in science we have clear objectives. You actually contrasted it a bit with mathematics. And so the clear objective that I see being taken is sort of you have to predict the future. Now, I've had discussions with colleagues in the machine learning world, of course. Let's say you want to predict the motion of the planets. So you could train a deep net to predict probably motions of planets or stars. You wouldn't actually get at Newton's laws or at the model of our universe. And my sense is that it's very different. So my sense is, yes, a deep net could probably predict where Venus is going to be in the sky at some point. But it doesn't actually get us at the laws of physics. So it's a little bit related to the reports of, oh, we can, rediscovers F is m times a, Newton's law. But that assumes that you put in the concepts, the force, mass, acceleration, friction on Earth doesn't matter, for example. Objects that are in motion will stay in motion. The conceptual framework is a much different task than fitting the parameters. So I think the objective of what a system should learn doesn't seem to be all that clear. If you say, well, all you need is prediction.
Well, I think ultimately science is about prediction. Of course, this deep net, which predicts what happened to Venus, will not predict what will happen to an apple when it falls from a tree. That's.
But that's exactly my problem. I guess so. That's the big insight that Newton brought, of course.
I accept that. Of course, it's about the simplicity of the explanation as well. There is, of course, if you're a real Bayesian, what you should do, in principle, is to have all the possible laws and weight them by your belief in them and sum them up, but that's not what science does. So for some reason, we think that there's only one explanation there rather than sort of doing the proper Bayesian thing. And it's not so clear why we do that as scientists.
But you are okay so you work on a planet and you predict where Venus is, you're predict that an apple falls from a tree. I think that's part of the key of science, that we unify all these things.
I think that's something that we'll pick up, I think, through the rest of it. We don't have much time for questions. Anthony?
So I want to pick up a little bit on Eirini's comment about serendipity. It seems to me that we need some new words here. So we're talking about science, and we probably all were introduced to the scientific method, observing the universe and asking an important question and so forth. But a lot of that comes from these human things like curiosity and serendipity and the ability to make your research relevant to others, to excite people, hearts and minds. Those are not typically machine-like things. And so it seems to me that there is a juxtaposition between the very positivistic thinking, there's an answer out there, I'm going to go calculate the mass of the electron, and then the constructivist thing, I want to understand what happens at the event horizon of a black hole. That second one is not a question in the sense of I can prove when I've answered it. It's a question that once I study it allows me to ask more questions. So I love the idea that you proposed about human machine. I wrote the term down and I lost it already. Human computer teams. I love that idea that on a team, we all have a different role and we're not all just trying to get the ball to the end of the field. We all have different roles. Somebody has to protect the goal. There's referees. We have rules. We have roles. We have ways of objecting when we think things are wrong. So it seems to me that we need new words for this thing that you're calling robotic science, because it's not the same science that we sort of constructivist thinking allows us to evolve. It's more of a very specific usage of the word science, which is completely appropriate, but different. And it seems to me that we need to have room for both.
Yeah, so actually one of the motivations I didn't discuss for doing this is to try to understand science. That was my original motivation. It's the idea of if you can build a machine, you sort of understand better what you're actually doing. So it's making things more clear and in the scientific process. Is a motivation.
I'd love to let questions go on because these are good. But we are, I think it's over time to really move on to the next speaker now. So those of you still got your hands up, please put your question, either write it down and don't forget it, or put it in the chat, because we do have the opportunity to have discussion at the end. So don't forget the question you were going to ask, please. And so either put it in the chat now and we'll get back to it, or write it down and ask it later on. So sorry we couldn't talk about it now, but please ask it again later. So now we move on to get the right person here. Aleks. No, I think Eirini is going to actually give the talk here. So Eirini is a systems architect designer, Center for Collective Intelligence Design at Nesta. She'll probably well explain what Nesta is about. Yep. So Eirini, you have the floor.
Cheers. Thank you, Jeremy. Can you see my screen?
Slide is looking good, yes.
Great.
This is what Nesta is.
Yes, so Nesta is a global innovation foundation. It's been existing in the UK for 30 years now. So we design, test, and build different social innovations. Today, I'm joined by my colleague, Aleks. We are part of the collective intelligence design team, and we started design and build systems that combine human and machine intelligence to tackle social challenges. Let me explain a little bit what we mean by collective intelligence. We mean this emergent property of groups that is created from the collaboration, collective efforts, or competition of different individuals. It's a really multidisciplinary field. It draws from different disciplines and methods like citizen engagement, collective decision-making, crowdsourcing, human computation, prediction markets, among other things. And obviously, it's not new, but what is increasingly new in collective intelligence research is how we can create an enhanced capacity through combining human and machine intelligence. That is, use technologies and new sources of data to connect more of us together at a much greater scale in entirely new ways. So today we wanted to have a conversation about the future of machine and human intelligence at the knowledge frontier. And you may ask, why now? Well, each day researchers publish more than 4,000 scientific papers just in biomedicine. While the number of publications grows exponentially, the novel ideas that we produce expands only linearly. Also across fields, the amount of effort and money that is required to innovate is actually growing, which means that maybe science is not advancing as much as quickly as we expect. So scientists have responded to that, the expansion of science by making larger collaborations and by organizing their work into more specialties. But even within a single discipline, traditional mechanisms of staying up to speed and navigating the knowledge frontier have some limitations. So textbooks are slow, literature reviews may be ad hoc and overlook some disciplines. And I think that was mentioned in some presentations this week, that this fragmentation leads to a greater explosion of unnoticed and undiscovered public knowledge. So these knowledge fragments may be, for example, undrawn conclusions, or analogous problems, or hidden correlations, or even kind of discarded findings from previous literature, but we may not have systematic ways to resurrect them and use them today. So our proposal is that we need, our provocation for today is that we need to reimagine our tools and incentive systems that help researchers, funders, and policymakers gain this shared understanding of the current state of scientific knowledge and then prioritize research at the knowledge frontier. And of course, I think we've discussed that a little bit in previous presentations. In the last decade, machine learning and deep learning really now help us make sense of all the data and discover new connections in scientific publications. But on the other hand, humans have those unique abilities, such as creativity, intuition, contextualization, that cannot be at that stage substituted. So moving forward, we agree with Russ, that I think I was mentioning in your presentation, that we need to combine the best of both worlds to be able to explore that complexity. So in our presentation today, we will explore some tools that harness collective and machine intelligence to enable cross-field navigation of scientific evidence, more efficient synthesis and validation of knowledge, as well as knowledge transfer between individuals, teams, and disciplines. And we will offer some suggestions for discussion. So to start with, we need to better encode knowledge. Scientific knowledge consists of concepts and relationships currently in papers, patents, software, and other artifacts. They're not so easy and clean to make sense of, even less so with graphics and metadata, sorry, with images and symbols and other semantics, which is even less difficult for machines to parse. But in recent years, it's becoming increasingly more possible to represent scholarly knowledge in machine actionable form. So far, the emphasis has been on linking data and metadata about articles and people, But we see really interesting efforts, for example, Project WPEG, that uses AI to infer the data sets in a publication and then uses the wisdom of the crowd, people to basically validate whether reject or validate these data set annotations. The other part is how we discover knowledge. Once we include those pieces of knowledge, we need to be able to search them at the right level of representation. So again, we see lots of advances in natural language processing, NLP, text mining, and information retrieval that helps researchers find scientific information better. We see citation analysis that are much more capable at identifying intersections and emerging trends between databases. We see a lot of really good work on improved representation learning and extreme summarization of scholarly information that alleviates some of the information overload. And a good example here is open knowledge maps. It's a notable example of human-AI collaboration, which clusters papers in similar subfields into bubbles based on keywords, datasets, and research software, and then allows scientists, hundreds of scientists, to create, edit, and update their own knowledge maps. But increasingly, what we think is really interesting here is that we can now extract scientific information in a much more granular level. So we can extract now problems, hypotheses, methods, findings from papers. And that has been possible partly because of advances in transformer language models like SciBird and BioBird that create much more accurate semantic representations of scientific concepts. Usually, however, these models are pre-trained, these language representations, by domain experts. So it's difficult to generalize outside of the domains that they have been developed. But we think this limitation, again, can be addressed by harnessing the pools of expertise by technical experts and scientists and policymakers. And a good example of that is a Track COVID challenge by Allen AI, where basically extracts useful information from publications and Twitter and library searches, and then it collects rankings and relevant judgments over those paper pools from different medical domain experts and uses them to increase the accuracy of those search algorithms. So we see a lot of potential for expanding that across the sciences, not just biomedicine. And lastly, I mean, scientific discovery is driven by analogies in different fields, which our machines cannot really do now. But we see really interesting experiments like Project Solvent, where basically it asks people to annotate methods and findings of different papers to train algorithms to be able to find analogies in different papers. So you can query a paper, give me one method with the same results, or give me the same results with different methods across like a bunch of different publications. So when relevant public knowledge is encoded and discovered, then it needs to be synthesized. And we see a lot of really interesting work on knowledge representation, which allows scholarly information to be structured as semantically rich knowledge graphs. Currently, more automatic approaches of doing those graphs can achieve moderate accuracy and have limited coverage. When they exist, they describe scholarly knowledge in specific fields like mathematics or chemistry or the life sciences. But we envision a much broader project, a knowledge network for science that can enable this synchronized curation and augmentation of knowledge. So near future, we want to see near future knowledge synthesis systems that continuously navigate knowledge and integrate theories and empirical evidence. Design and interfaces are really important, obviously, for navigating that. So we want to see more of that so that scientists and policymakers can basically describe constructs and make roadmaps together. And the resulting knowledge graph can be used to identify relationships between different knowledge entities, such as methods or experiment data, in much more granular and big ways that we do now. But due to the complexity of this task, the population of comprehensive ontology, of course, would require domain and ontology experts. And a really good example that we've seen is the Open Research Content Graph that combines human and machine intelligence, where basically organizes and connects scholarly knowledge using crowdsourced contributions from different researchers who acquire, curate, and publish this knowledge. Lastly, to achieve those semantically rich knowledge graphs, we need to enrich our documents. We see collective intelligence approaches on article annotation in a very decentralized way, like Project Dokli, and other initiatives like micropublications, which is a new model to represent scientific arguments semantically. Well, lastly, of course, this knowledge synthesis infrastructure, the components that I just described, cannot be complete without curation and quality assurance from domain experts and librarians. These collective processes of quality assurance are increasingly important because, in many disciplines, it's hard to replicate findings. We have flawed experimental designs, small sample sizes, and so on. But increasingly, I don't know if you follow the meta science work, there's a lot of interesting automated ways to check papers for publications and limitations, automatically categorize scientific uncertainty in papers, or find other faults. And here we think that those efforts can be augmented by more distributed peer review processes like Project Ivor is a good example, or crowdsourcing intelligence from experts that are able to detect and point the evidence containing parts of publications. So we can then train algorithms to find that across papers and across fields. So, well, in summary, never in recent history did we have all the tools in our hands to navigate knowledge and connect those undiscovered pieces of scientific understanding. So how the question that we want to discuss today, like put to the conversation, is how do we move from the more low-hanging fruit of using AI for efficiency in processing those documents at scale towards a more complex and imaginative human AI teaming for science and innovation challenges. We will offer 3 propositions, but we are very open to a discussion here. So we think that we need a more finer grained and machine actionable representation of scholarly knowledge. This infrastructure should be able to support knowledge curation, publicis, and synthesis by both humans and machines. There's some really interesting work, and we think there should be more on scientific NLP. So scholarly outputs have unique challenges that necessitate NLP processing methods optimized for this domain. So we would like to invite research funders to consider having a more extensive R&D program on that, or even thinking other interesting dimensions of this question about what is, for example, the process for collective data annotation or collaborative knowledge graph development, or deciding which approaches, humans versus machines, are best suited to populate those knowledge graphs. And another interesting research direction, which we haven't seen so much of, is creating the tools that help optimize collective potential of scientific teams and mass collaborations. So this will rely more on research into cooperative AI systems that enhance group decision-making in scientific teams, which we think lags more behind in terms of the funding that has gone in that space. The second, we think, a proposal that can lead us to that future is rethinking the incentives to do that. So currently, institutional, educational, and social factors inhibit this knowledge integration. So to address that, some have argued for creating a new market for knowledge synthesis workers, or more integrative PhD programs based on that knowledge synthesis. That we agree with that, and we are inviting research councils and policymakers working on R&D to consider those propositions, but also consider supporting what we would call the applied meta scientists, like those people who curate and maintain. Yes, I'm finishing up. Thank you. This information infrastructure and can build bridges between the public, academia, and industry. Other really interesting incentives that can be used here is prizes and competitions. One good example, I think our friends at Illicit are involved there, or they may be involved in really interesting things. They're speaking today after me. It's Science Forecast, which is like Kaggle, but for science for science algorithms, and it incentivizes the development of algorithms that capture the growth of scientific concepts and forecast which concepts may arise in the next few years. And the last point that we wanted to make is that we need more collaboration between academia, government, and industry to create those tools for better machine and human understanding of scientific knowledge. There's a lot of conversation in the US about revitalizing the research infrastructure. Recently in the UK, there have been some calls about establishing new institutions like the Atlas Institute, who will be tasked with fully mapping the world of scientific knowledge and identifying gaps. But we think it's really important to have those collaborations because they will allow a more democratized access to the latest science algorithms, maintain this common database, code base for researchers and even non-technical practitioners to navigate the knowledge frontier together. So I'll summarize. some of the biggest challenges, as Ross mentioned, are cross-disciplinary and require interdisciplinary collaboration to solve. Not being able to catch up or remain on isolated knowledge islands risks slow down scientific progress further. So we believe that our scientific and policy networks require new tools, incentives, and institutional structures to track knowledge across fields and prioritize challenges across disciplines. We've seen a wide spectrum of health, economic, and social challenges who have benefited by those mind-machine partnerships, if you want new words. I don't know if that makes a case for that. But in the current trajectory, we think that only AI will be able to keep up and make sense of this ever-growing literature. So yeah, productive human AI collaborations need to harness best of both worlds to allow scientists to prioritize and do responsible R&D. So I'll stop here. I hope I'm on time. And yeah, looking forward to the discussion and your questions.
Thank you very much, Eirini. Perfect timing. Certainly some things, ideas I'd like to pick up towards the end will be the issue of knowledge that's not even in a form yet capturable because it's in legacy form of handwritten notes or tacit knowledge in the presence of a few individuals who are about to retire and this sort of thing. So I think that's an area we're working on ourselves. So can pick that up maybe later. For questions, suddenly everybody everywhere I had. So Gary, I don't know if that's a legacy hand that's up because I know you've been active in the chat, but.
I think that the key issue really is the one that Bart pointed to around knowledge. In order to enable the vision that we're talking about, we have to be able to explicitly communicate hypotheses to the machines, and they have to be able to explicitly reason over them. They can reason over hypotheses that we don't understand, and that can be useful. And AlphaFold is a really good example of that, where we can understand a little bit of what it does, but we don't really understand how it gets there. The representations are actually different from a standard convolutional neural network. They're actually pretty tuned to three-dimensional geometry in order to be able to do the protein folding. And that's useful and it's a good step. But we don't have systems where we can just say, hey, this is Newton's law and let's work with that. I mean, there's some work around that. But my dream is that the systems that we're talking about should be able to absorb all the text in Wikipedia, for example, and just apply that to whatever problem we want them to work on. And we don't have anything that can read well enough to do that. And we don't have anything that can generally reason well enough. And Psych by Doug Lennett maybe can do a little bit of that in certain domains, but we don't have a general solution to being able to reason about scientific knowledge. So in some ways it feels like we're really close. We've made tremendous progress in the last few years, but there is this real gating mechanism, which is how do you get from a distributional statistical sense of correlations to this abstraction, which is what scientists reason over, at least part of what scientists reason over. On that side, we haven't made as much progress. And we should be thinking about what do we do in order to make that progress? How do we incentivize people? So there was also, I think, a reference to advertising and so forth. Like the problems that advertisers need to solve in terms of recommending news feeds or things like that are not the problems about knowledge that are important for our discussion.
100%, yeah.
Of course, I do hope that the AI system will take the note that we take to the students that Wikipedia is great, but be careful.
Well, I mean, we could do even better, but it's a good starting, benchmark. Exactly. Can you read a Wikipedia page and not just repeat what's in the boxes, but actually take that knowledge that is there and apply it to a problem?
Absolutely. I think Alistair.
Yeah, thanks very much, Eirini. That was fascinating. So my question is about, well, it really comes from in preparing for this workshop, I approached the National Science Foundation, amongst others, because I'd heard that they were using AI systems to help the selection of peer reviewers. And when I queried them more closely, it was really marginal and the persons involved didn't really want to present, etc. So I'm just wondering whether these sort of exciting leading edge possibilities for using collective intelligence, what do you think about the chances of really incorporating them into the sort of mainstream processes in science systems? How they seem quite radical, and some of them, which is a good thing, but may upset the cart in the science systems, I can imagine, which seem to be quite conservative. So what do you see as the likely or possible further diffusion and rollout of these systems?
That's a great question, and one we at Nesta we work quite a lot with governments and public policy, so we're thinking a lot about those questions. We see those fragments, like really interesting research, for example, from Allen AI Institute, but it's not being uptaken from national research organizations, right? As you pointed out, and we think it requires more targeted research programs for more time, so that more people can actually uptake them. So we've seen that it worked well with Archive or with Zenil, like how we capture data from publications. Like it requires long-term support of those tools and those research agendas to be uptaken by scientists.
That's a really important issue. But I thought the mathematics provers could prove the associativity of these things, but you may have something else to say at this point.
Yeah. No, I love to put that up because they really can't, and it caught me by surprise. I guess I worked a lot on propositional theorem proving for my career, and we went to first order theorem proving. So if you just put in Peano's axioms for the natural number, most theorem provers, I would claim all of them, that are fully automatic can actually not show that x plus y equals y plus x. You have to put in the right induction hypothesis. You have to formulate it carefully. You can get it to do it, but you have to guide it by hand. And so my point there is more that actually, mentioned this hybrid between machine and human might actually be very important. Even in mathematics, I guess we went largely to interactive theorem proving, where the human and the machine works together. My group tries to do it fully automatic, and it's just so surprising how difficult that is. And then I have the sense, well, if my AI system can't yet show that x plus y equals y plus x from Peano's axioms, so it's not given as a fact, it has to derive it. It would have a hard time to do good physics or certain areas of science or engineering. So I just want to point out that sometimes we overestimate the capabilities in terms of reasoning of what's currently feasible. So,
any other questions for Eirini? So, I mean, maybe the role of Nesta, I think, is to indeed encourage and suggest where resources might go and act to them. I mean, do you think we'd be successful in encouraging globally the authorities to invest in the right areas so that the knowledge circulates appropriately, that human and computer systems do work together? As some of you know, I look after this network, which we refer to as augmented intelligence of scientific discovery, along with other various AI in there, because of this need for people and computers and equipment and data and whatever to work together. But what do you think the prospects in the near term of persuading the authorities that this is where money should be put?
So I think it's a lot about creating the evidence by having more experiments. So that's what we've done in our team. We have funded a series in the past 3 years of collective intelligence experiments that test different hypotheses across different fields. And perhaps my colleague Aleks can jump into that and share a bit more about what we've learned, because we are trying to communicate this with policymakers and see how we can progress the field together. But I'll pass it over to Aleks.
Yeah,
thanks, Eirini. I'll be brief. I think just quickly on your question there, I think the proof of the success of that experiments program is that the second round, when we did it, we were able to attract very significant foundations to create a pooled fund. So our second round of collective intelligence grants, which were experiments in human-machine collaboration, were supported by Wellcome Trust, Omidyar Foundation, Cloudera, which now is the Patrick McGovern, I think, Foundation. So I think there's a lot of interest, but to be honest, it is still quite piecemeal. And so we haven't seen that kind of large-scale commitment to AI funding that is also looking at the kind of collective human intelligence role in AI. And that's what we're trying to, I guess, get to through demonstrating some of the evidence through the experiments program. And I mean, we've had a whole range of experiments that are quite relevant to the discussion of this meeting, which look at the search functionality to improve knowledge discovery, to improve collaboration between different participants who are on a collaboration network or an innovation kind of network. Some that I can mention, for example, are in our latest grant funding round, we supported a team that was looking at new types of recommendation engines that could be based on serendipity rather than predetermined patterns in order to support groups of innovators coming up with new ideas. Others have looked at building knowledge graphs based on crowd wisdom of medical professionals to address open-ended problems. So we are trying to get some of the momentum behind these questions and generate some of that initial evidence to encourage others to do the same. But I think the more that we can unite with others, perhaps the people in this room to get that message across, the more successful we'll be.
Thank you very much. I would certainly want to chase up and have a look at your reports and have a chat with you about what we might propose for what we continue to do. But I'd also say that from, if you like, that's kind of top down. And at one level, we're also trying, in my discipline of chemistry, trying bottom up. We are changing the nature of what might be considered to be chemistry, or the way chemistry is done, to meet it coming in the other direction, that chemistry will be done in this way. So, you know, it's become much more data driven over time already, but these other more powerful techniques in some senses are not yet embedded in undergraduate disciplines, but they soon will be. So I think, you know, things are transforming from both ends. But maybe it would be good to actually try and link that up a bit more. But hopefully we'll produce a new generation of researchers who will not think of this as something different, but will think of it as something, well, of course you do it this way. Thank you very much, Eirini, again, for a really great talk, and for Aleks for the support there. And I'm definitely going to be looking at the Nesta outputs again. I haven't looked recent for a few years, so it's good to get the reminder of that being there. Thank you. If we think those questions again, anybody who didn't get to ask their question, please remember it and bring it in later on. So I've noticed a really interesting thing, particularly for people like me whose names begin with J, with a J, that all the next speakers all are J's. So clearly there's something very important here. So I was very disappointed that with the later set of elements that were approved some years ago, a few years ago, and Nihonium was created, and to honor the Japanese researchers, that it didn't have the word Japan in it with a J. I mean, it had the Japanese version, and correctly should be, because I can't build my name out of chemical elements, which is a very disappointing, and I had high hopes of this. But Jungwon is the co-founder and chief operating officer of OUT, I think it is, and is going to talk about AI research assistants. I definitely want one of these to help with my human research assistants. Over to you.
Thanks, Jeremy. Thank you, everyone, for coming and giving me the chance to speak. I'm really excited to talk next because it seems like my presentation will be able to build on a little bit of some of the conversations and threads that have already emerged. So like Jeremy said, my name is Jungwon. I'm the CEO and co-founder of AUT. AUT is a machine learning research lab whose mission is to automate and scale open-ended reasoning. We want the complex reasoning that you are able to do with great care, expertise, and time to be more accessible in a variety of life contexts, and just to really, improving that reasoning will kind of move the world forward across many different domains. And to that end, we're building Elicit, which is a research assistant. Elicit uses language models to automate parts of the research process, language models like GPT-3. So I'll bring a little bit of a practitioner's perspective, which I hope can also anchor our conversations on what models can and cannot do. And then from there, we can get creative and extrapolate out into the future. I'll start by talking a little bit about language models, just to make sure we have some basic context. And then I'll give a few demos of Elicit, and then we can take it from there, talk about the future. So language models at a high level, for those of you who don't know, are models that are trained basically on massive amounts of text on the internet. So I'm specifically going to be talking about GPT-3, again, a very specific type of AI. GPT-3 was released last year. It was trained on something like 2 trillion characters, a lot of text on the internet. I think that ends up being about hundreds of billions of words. And it's designed to, given a sequence of words, predict the next set of words, or tokens, which are kind of subsets of words, but something like that you can kind of heuristically think of as words. And what this means is that it is, compared to kind of previous forms of natural language processing, has a much more semantic and associative reasoning than before. So it's not as keyword specific, but like as Gary has pointed out, it's still not. It is still associative. There are limits to associative reasoning, right? So it's not clear that it has clear causal models or world models. It was quite, GPT-3 when it came out was quite groundbreaking, because it demonstrated that these pre-trained models are able to perform well on a variety of texts. So again, in NLP, like kind of pre-trained models, you have very task-specific models, like a model for summarization, a model for sentiment analysis of this specific type of data set. And then these large pre-trained models demonstrated ability to do many of those tasks without being trained for that task specifically. So kind of starting to get into more general purpose reasoning. So basically the way I think about it is these models are kind of pretty good at reading and writing or speaking English. But they still represent the distribution of the internet. So something like the average internet user, and we need to get them to be useful, for a researcher who's very, very expert, right? They are a very small percentage of the internet population. So the trick is really, how do we take this generalist reasoner that has a capacity to become an expert and really tease out those expert qualities and then improve it and train it and teach it to learn a little bit better. So I'll start just to kind of ground our intuitions with a quick demo of GPT-3, just to explain what I mean. So like I said, it'll take a sequence of text and try to predict what comes after it. So for example, if I say, today I'm going to give a talk to the OECD about the impact of AI in science. This is GPT-3. This is kind of the OpenAI playground. And this is the kind of model-based completion of it. And I'm going to try to give a more positive message, I think, than some of the other people who have spoken about this topic. So I'm going to try to contrast today this negative. I had no idea what this was going to say. I tried it before the talk, and it said something completely different. But you can see that it's like, someone could have sent you this, right? I could have sent you this email. So I think this is where people really started to be amazed by the capabilities of this model. So that's basically how it works. It takes this prompt and then completes it with these sentences. But of course, it can definitely break down, and sometimes it makes things up. And really, the more it generates, the more kind of unwieldy it gets. So that's basically how this model works. And then Elicit uses these language models and tries to, we're trying to find the intersection of what these models are capable of and what's actually useful for researchers. And the way we do that, because these models are so flexible, is we built a sequence of tasks. There are just a bunch of different tasks that use these language models. And some of them are kind of more atomic than others. But ultimately, our vision is that researchers in 5-10 years will be able to kind of take these building blocks of reasoning that use, some ML and some maybe other basic infrastructure, some types of ML or AI that are kind of much broader than others, and automate parts of their workflow in a very bespoke way, leaving them in this kind of architect and position and research methodology divisor position. I'll start with a couple of more simple tasks and then get to our core task, which is around literature review. Again, just to kind of scale up the kind of complexity of what I'm showing here. So the first thing I'm going to start with is brainstorming research questions. If you've seen GPT-3 demos on Twitter, you'll see that GPT-3, some of the most common applications of language models is around brainstorming and creativity, because they're so fast and they are less anchored by social norms. So in this case, this is a task that researchers use to kind of get out of their ruts and explore like adjacent questions. So I'll start with, what is the impact of creatine on cognition? Let's say this is a question I'm interested in looking into, but I want to think about what adjacent questions are here. How might I start to break this question down? And now these language models are going to suggest to me other research questions in this space. This one is kind of a rephrasing of mine. What is the relationship between creatine supplementation and cognitive abilities? I might get rid of that. What dose of creatine does bodybuilding doses correspond to? That's kind of interesting. Maybe that means, maybe I don't want to get into the bodybuilding phase, but that's probably not really relevant. So you can see how some of these results are not relevant, right? So the researcher still needs to be in a position of giving feedback. I'm going to delete the results that are not relevant. How do the impacts of creatine vary by age, sex, neurodiversity, training level, et cetera? That is interesting. That's taking my question, which is kind of underspecified, and starting to break it down into dimensions of demographics. This is kind of redundant, so I'll get rid of that. How much do people benefit? That's also maybe interesting to specify. How much of an impact do I want to observe? How many articles are published that are actually supporting this? Maybe that's one way of thinking about the kind of confidence we have in this finding. This, I can specifically look at RCTs, and this one kind of seems redundant. And then, so this is, you can see what we've enabled is, allowing the researcher to give feedback on the results they like, get rid of the ones they don't like. And now if they click this button called show more like starred, the model will start to update more towards the answers and the results that the user has selected, and kind of away from the others. So it'll generate more around safety. This is redundant, so I'll get rid of this one. I don't know what this is. I've never heard of it. And then this is also an interesting question. Does creatine supplementation act by improving the supply of energy to the brain, or by supporting neuronal function more generally? So I really had no idea. I don't know anything about creatine and its impact on cognition. I don't take creatine, but now I'm starting to have a better sense of how I might think about this question if I needed to look into it. That's one task. And so just to give you a little bit of context, the way it is trained is we have these kind of pre-trained GPT-3, right, which has 175 billion parameters. But then we give it a couple of examples for this specific type of task, and use what is called a few-shot learning to tell monster GPT-3 do this specific thing. So these are some of the kind of training examples that are going into the prompt, so that GPT-3 knows when you get this type of research question, what we want to get back are these kind of more specific types of sub-questions. And this was our approach at trying to get GPT-3 to slightly more formal reasoning. We are interested in having these models do actual kind of complete decompositions where the sub-questions very clearly, if answered, answer the overall question. But right now we're at a place where that has to be much more fluid and associative. So these are not kind of like a mutually exclusive, completely exhaustive list of sub-questions. There's a different way, I think. Another thing that we see is maybe the fundamental interface with these models can look different. And this task kind of demonstrates that. So I'm going to ask the same question again, impact of creatine on cognition. This task is called help me be more specific. And it will start, you'll start to see that the model can kind of mirror an advisor or a helpful peer here. So this is the first one was kind of generating sub questions. This one is somebody is asking you questions that might prompt you to think more carefully. So what is cognition? It's kind of pointing out that cognition is underdefined in this question. How much creatine do you have to take to see an effect? What does impact mean? I don't really understand what this one is, so I'll get rid of it. This one seems irrelevant, so I'll get rid of it. What type of cognition? Are we talking about human cognition or animal cognition? What's a placebo in this question? That's kind of interesting, but a bit strangely worded. So maybe I'll take some of these and then again, show more like starred. To specify impact, how much performance boost are we talking about? What is the level of cognition we're testing? Let's make this more specific. Are we talking about healthy people? So this is it's not groundbreaking, right? These are very basic questions. These are questions that we should be asking, but sometimes when you kind of stuck in a rut, it's a really quick way to get out of it. For younger researchers, perhaps it's a good way to anticipate conversations with their advisor and just kind of very quickly go through kind of, good best practices around thinking through questions. It's pretty easy to create these tasks. So we have one called method divisor that a user created. And this one is, let's see, creatine to improve cognition. It'll take some goal and suggest steps for getting there. So now the model is saying, create a schedule to take the supplements every day, look up information regarding what effects it has, how much creatine should I take a supplement containing creatine, read online testimonials, et cetera. So these are kind of initial explorations into what models might be able to help us with. So in the future, we might be able to have these models suggest, processes or research methodologies that researchers can kind of evaluate, especially, with more feedback and kind of training specifically for that purpose. They might be able to help with question formulation or at least brainstorming. They might be able to help the researcher specify their questions more precisely or think more clearly. Again, it's still the researcher doing most of the work, right? But these are tools that are kind of amplifying them, assisting them, and pushing the researcher forward. The primary task we're focused on now is literature review. So this takes some of those subtasks that I showed and starts to kind of put them together into a more complicated workflow. So now if I do, what is the impact of creatine on cognition? What this will do is it'll actually search through existing scholarly databases, in this case, Semantic Scholar, to find relevant papers. And it'll return claims that the papers are making based on the abstract. So it's kind of summarizing the abstract and also directly trying to answer the question. Creatine supplementation influences brain functioning, has a positive impact on cognition in vegetarians. Oral creatine administration may improve short-term memory. And so this is where what we found is that you really do, at least today, want to kind of tie these models together with like real world databases or ground truths, because otherwise the models can just kind of make things up. And so very much anchoring, this is a human has done careful peer reviewed study on creatine and vegetarian and the impact on vegetarians here. And the model is just kind of trying to rephrase some of the statements in this abstract in a way that is a little bit more legible and accessible to the user. So we hope that this will both allow research to be more accessible, kind of to what Eirini was saying, taking it away from being about papers and more about ideas and claims, and also at the same time kind of show more perspectives to the researcher. So this one says oral creatine may help older adults with cognition issues. This one says it might not. This one's an RCT, this one's a review. So more quickly kind of getting to different perspectives and being able to review papers faster. We've started experimenting with tags here. So these are more simple models tagging, randomized control trials, review papers, systematic review papers, because review papers tend to be a good way to get started in a new domain. And then, some people are explicitly looking for interventions in RCTs. But we've had users request much more flexible and customized versions of these tags. And so are experimenting with kind of ways to do that in a more open-ended, user-driven, customized way. Again, kind of putting the researcher in the position of research architect. So, let them think about, do I want to find reviews? Do I want to find longitudinal studies? Do I want to find, surveys, whatever? And then be able to let the machine kind of canvas all of the literature and then prepare that in a way that is pretty easy for the researcher to review. And then, that's kind of for the research creator, but also for research consumers. These models have the potential to make research much more accessible by, kind of presenting things in terms of the claims, et cetera. And then for this one, if you do show more like start, you'll kind of move along the citation trail. So let's see if I focus on the ones that talk about specific populations. And then show more like start, I'll incorporate in my ranking papers that cited these papers and were cited by these papers. So it's a combination of using both the kind of language models and AI with existing technology and software infrastructure. And then if you compare, I think if you compare it to kind of existing tools, like let's say we run this on Google Scholar, I think existing tools maybe anchor too much on the paper as a unit of information and make it a little bit too hard to get to the answer. So the snippets are like kind of hard to process, and there are a lot of papers to read through. Many researchers have horror stories of reading through like lots of pages only to realize it was kind of irrelevant. Semantic Scholar is the same thing. It's not really designed to answer questions. It's more designed to find papers. So a lot of their queries are titles of papers. Google is a little bit better at question answering, but it's, that's not designed to be scholarly. So it'll give you this knowledge box, but it's again, only from one paper. And then it's kind of hard to evaluate how trustworthy these different claims are. And then if you just ask GPT-3, it'll answer something, but really not give you a chance to figure out how trustworthy it is. Like, I don't even know, like, this is, well, I guess in this case it doesn't. Maybe let me try. The impact of creatine is. So I think like the GPT-3 model is kind of what, so this is, it sounds convincing. It even has fake references here, but there's no way to know how legitimate this is, right? And I think this is kind of the model of artificial intelligence that people are afraid of, this like Wizard of Oz oracle that gives us all the answers, but it's actually been secretly optimizing for the wrong thing, that people kind of trust blindly. And I really think that's not what we need. We need something at the intersection of existing tools, which require a lot of work, but are also legible, and something like this, which doesn't allow you to, doesn't have scaffolding around evaluating trustworthiness, but is obviously a lot more accessible. That's really what we're hoping to accomplish with Elicit. So at a high level, our vision is to use these models, as much as we can, and we don't really know where the limits of these models are. If we need to supplement them with existing tools or people or human knowledge or experts, we will. But really try and understand what are the core tasks that researchers perform, where can models or different types of kind of engineering, software engineering support that, and then how do we build up an ecosystem where, and a product where the researcher can really sit in the research design, research architect position to put those different approaches together and start to think at a more meta level about what they are doing, share those processes with others, and kind of, and take a much more, and basically be amplified and take a more kind of systematic approach supported by these tools.
Thank you very much indeed. So I'm now very worried when we set things for our students. We already check to see whether or not they've been copied from Google or Wikipedia or whatever, but now I'm worried that there's an alternative route, and I can see the next generation of your tools is going, I'm going to type something in like that as a question and get a very instructive answer, not just guidance. If they use the tool to get the guidance to the papers to read, that's fine for the students, no problem at all. But if it answers it for them, so we may have to ask whether the text that is submitted could have been written by one of these engines. But really interesting. Bart.
I'm just curious what you think about the GPT-3 model is always very impressive. What do you think in terms of whether the system truly understands the meaning of the term? So I always like to sort of give a little example. If I ask my Alexa whether it rains outside, it often will give the right answer, but Alexa has no clue what rain is. To what extent do you feel that GPT-3 gets at the real semantics as we get them when we hear words and sentences?
Yeah, it's tricky because I think that in some ways we can't ever inherently know. We can only observe what it does and make some evaluation. And definitely between GPT-2 and GPT-3, the things that GPT-3 says are much more things in line with understanding things. It was much less coherent with GPT-2. And so I think we can expect that whatever GPT-4 does will seem to us even more like it is understanding things than GPT-3 does. And I think there's some question around like, how confident can we be that humans understand the things they talk about? And I think there are definitely certain cases where people will use certain words or say certain things without necessarily understanding the details of them as well.
I'll definitely back that.
Yeah.
And yes,
okay.
Anthony, I think you were next.
Yes, I was trying to find the unmute button. Fascinating presentation, really appreciate it. I have sort of two sides of this that I'd be interested in your thoughts on. One, you were very careful to talk about the fact that the learning, and I'll put that learning in quotes, the learning or the ingestion of corpora of data here comes from someplace. And the bigger that place is, the more sort of normalized it tends to get to the way the articulations in that place go. And I think that's a perfect grounding for this. The observable use of language. We've done a lot of work in my group around confounding characteristics of language, like neologism or sarcasm. The example I use all the time is if you look at the word Trump, 10 years ago, it's a verb, and now it's more likely to be a proper noun. These sorts of things, when we're at the edge of morphology of language, we need a different approach to realize that we're experiencing that. And certainly you can realize perturbation, but not necessarily know what to do with it. That's the one side of the record. And the other side of the record is fascinating opportunity here to use this sort of capability to detect obfuscation or which of these is not like the others, where the unusual corner is that we need to pay attention to. So I was wondering if you could talk either about confounding characteristics of language at the edge of use, or about using this to find the unusual.
I can definitely talk to the former. I think that's a real problem. So one thing I forgot to mention is that GPT-3 was trained in 2019. So that's about the extent of its knowledge. It doesn't off the shelf understand COVID at all. It has never seen text around COVID. And so that was one of the limitations we ran into. And that's really where we see the need to pair it with other tools that might update and have caught on to these norms that changed more recently. So like obviously when we link it with, Semantic Scholar or other kind of external search where people are kind of creating new content that are more relevant, or if we kind of fine tune it, update the model based on more recent text or something that we think is more representative of the situation that we're interested in, there is an additional processing that has to happen there, definitely. Yeah.
Thank you.
Nico.
Yeah, so extremely impressive presentation, very, very interesting. So I'm wondering if you guys have thought about to what extent this facilitates and incentivizes exploratory research of truly unknown directions versus incremental science. And I'm really of two minds. Like in some ways, it seems like that tool is mostly useful for incremental work. I could be wrong. I mean, it was just a short demonstration.
Mm-hmm.
But then maybe the tool makes incremental research so easy that researchers no longer, like serious researchers, no longer want to pursue that. Maybe like, is there a parameter there that the user could switch? Is like, I want to explore super unpredictable directions, or have you guys thought about this?
Yes. So I think some of the brainstorming tasks can get much more creative, and you can create your own task to kind of be more exploratory and like kind of throw spaghetti on the wall. So I think there definitely it can help be like GPT-3 can be pretty weird. I think though our model currently is that to really explore good new research, it's not just about kind of having random ideas or having a random idea generator. Like that could maybe help you if you're expert enough, but probably it requires like a very deep, precise, fine-grained understanding and like detailed understanding, which GPT-3 can't do, and that's really where human expert researchers and scientists need to move the field forward. So for now, we're going to focus on let's try to take the work people are already doing and make it easier and faster, and give them more time to think about, to like synthesize and think about what is unknown, and hopefully free up the kind of brilliant minds to push the frontiers forward.
Thank you. Gary?
I just wanted to make a distinction about semantics and meaning and push on that a little bit. Bart started with. I think there are two issues. One is this stuff grounded in a way that the system actually understands what rain is? And I don't think we need to worry about that. I think my calculator doesn't understand what 9 is in some platonic ideal sense, and it's okay. But the symbols do have to serve their function in sufficiently abstract way such that the right computations follow. So if they're going to reason about nucleotides, they need to know certain things follow about nucleotides. Mm-hmm. It's okay if we humans import a bunch of semantics in there such that by the time we get to those symbols represent the things that we want them to do. That's how calculators work. That's how AlphaFold works. It's all good. We don't need to worry about the kind of mystical questions, but we do need reliable abstraction. So if you tell GPT-3, well, I played around with it a little bit. They wouldn't give me access for a couple of years, and I finally got some underground access recently. And I'm doing an art project that involves Socrates. And so I'm asking questions, and I say, to the machine in my role as Socrates, are you a person? And it says yes. And I say, are you a computer? And it says yes. And it doesn't understand the contradiction between those. If you had, there are many ways in which you could build a computer system that would actually represent them, but the way in which it's built is just statistically doing autocomplete, figuring next plausible things. And the word yes is plausible in both contexts, but there isn't a representation like there is for a number in a calculator. And so the system fails. And mm-hmm. There is a real upper bound on what that particular kind of system can do in consequence.
Yeah. Yeah. A version of this that we've also been thinking about is something around persistence. Like what is the kind of right level at which to maintain a persistent instance. So for example, across all the different tasks that we did today, should a version of GPT-3 have had that context so that as I refine my question, even in the next task, it understands the path I've been on and it's kind of bespoke to that, or like in your case, it understands that it just said it was a human and therefore it cannot say it was a computer next. So I think there are some really interesting questions there. Definitely haven't solved it on our side.
I just think it knows something you don't. And it was not inconsistent there. Eshi.
Hi. So I found your talk really fascinating, and I didn't know sensitivity existed before, so I'm definitely going to look into this. So my question is, sometimes the papers you need to be looking at are in a different field, and this is something we discussed a couple of days ago as well at this conference. So for example, like if you're developing deep learning for physics, somebody in biology might have solved the same problem, but they're using different words, and even the statistical terms they're using might be different. Have you thought about how you could bring this also into the system?
Yeah, I'm very interested in this actually, because a lot of researchers, like really so many requests for something like this. I think we would need to start with a couple of examples of, terms in one domain that correspond to similar analogies or have analogies in other domains. And I haven't found, everyone has a couple of examples, but I just haven't found a systematic source. So as soon as we find one, I think it'll be really easy to create a task in Elicit, because we have tasks that name things or suggest names for things. So I think its capability is there. We just need good examples too. Yeah.
I think that would be a great example for a Nesta study to assemble. Alistair.
Thanks very much, Jungwon. That was a wonderful presentation. I'm going to ask a very pedestrian question, which is, in your work with researchers, and given that the aim is to assist researchers, what do you know about any metrics as regards the impact of this system from what you've already seen or what you think might be coming in terms of compressing the time and resources involved in developing a research proposal?
Right now, most of it is kind of qualitative. I think we're still in the early stages of just getting richer feedback as opposed to something at a kind of metrics aggregate level. So a lot of it's around, I found this paper that I didn't find before. I decided to add these citations. I think over time we would be interested in maybe query for query, running it across kind of existing processes versus doing it in Elicit and comparing, how quickly we get researchers to insights. We've also talked about trying to replicate systematic reviews. I think that would be like a good context because of how structured they are, and because researchers kind of on an everyday basis do a less extreme version of systematic reviews. So because they're so well documented, we might take that on as a challenge, and that'll be a clear benchmark to compare against.
Thank you very much. I think we better move on now to next week. But thank you very much. You get the Golden Star for doing something in real time, actually risking running your programs for real, which I think again is a remarkable demonstration of the software, which I think we're all going to go and try and use now.
Yeah, please do. It's at elicit.org, so you can sign up there.
Excellent. Now I'm very encouraged by what you can already do. I think it's going to be very interesting to see that. So thank you very much again. And our next talk, we come back to some of the points I think that were brought up in some of the discussion about theorem proving, whether this will be mathematics or physics, we will see. And Joseph Urban, who's from the Czech Institute of Informatics, Robotics and Cybernetics. I think that covers about all the ITICS type things that you could possibly want to have here. So Joseph, over to you.
Thanks for the introduction. So I'll try to give you a bit about what we do for AI, sort of for mathematics and in particular for theorem proving. So if you need more, this has been a 5-year project that finished in October last year. This ERC project AI for Reason, which has some web pages and results to it. So I would start with this. Let me try to make it properly. Well, we're
seeing 1.5 of your slides on the screen.
Yeah,
which is good. It's better than only half a slide. That's much better.
I think this might be better.
That's perfect. Yes.
Oh, okay. So I would say like the sort of justification of some of that goes really to the beginnings of scientific revolution and to people like Leibniz. who came up with this strange vision that some people sort of continued after him, of this strange or massive reductionism of like what would be called physics today, or biology and chemistry, to mathematics, and to what would people eventually call logic or symbolic logic. So on this first slide, I have a picture from a really beautiful book called Logicomics about the life and research of Bertrand Russell. The particular situation when he sort of discovers that he shares the dream of reducing all of human problems and human sciences to mathematics and to ultimately to logic, which was one of the things that he really pushed a lot in his life. And this sort of program actually very seriously materialized in the beginning of the 20th century, and with people like Frege and Russell and Hilbert and Church, who actually really managed, like you could call it like the first big achievement in this very ambitious program. They really managed to put mathematics, basically to embed mathematics into symbolic logic. So it is a thing that is still sort of happening to mathematics and to mathematicians, but it seems like we can say that 100 years after that this has been sort of shown to be feasible in some sense, it now really materializes. And I would say the sort of side effect of symbolic logic, of the heavy development of symbolic logic in the beginning of the last century, was actually the invention of the universal Turing machine, or universal computing machine by Turing, and sort of the parallel development by Church, which are basically symbolic logic machines, even though many programmers and many AI people wouldn't know about it today. Like if you are doing some deep neural networks, you might have never heard about symbolic logic, and you might have never heard about the relation of symbolic logic to programming languages, for example. And the next interesting point is that Turing, who sort of was one of the founders of that, he actually, like some 20 years later, founded AI. Like he has this visionary paper in 1950, and at the end of it, he actually proposes learning machines, and he proposes something like AlphaZero. Actually, he says like how the machines could learn chess. So the one thing which happened, which started to happen in the 1950s and 1960s, is that like the mathematicians and the logicians, and also I would say the programmers or hackers at the time, considered mathematics and logic to be really one of the first targets, also because of this reductionism, of this sort of Hilbert style, Leibniz style reductionism. Like if we solve mathematics, maybe we have solved large parts or the hard parts of the other sciences like physics, for example. So the first AI program, as I heard it told, was this logic theorist by Newell and Simon, which was basically doing some sort of heuristic propositional theorem proving. And in the 60s, like people started to come up really with the idea of expressing more and more mathematics in sort of computerized languages, in formal mathematical languages. So the first major effort came from the Netherlands by De Bruin, that was the AutoML projects. But then really many systems developed, like LCF, Mizar, Hall, Koch, Isabelle, Lina, etc. And along with that, like I would say in the 60s, 70s, the topic of automated theorem proving became quite prominent in AI, and then sort of became less prominent because of the AI winter, etc. And people developed quite a few systems for really proving things automatically. Like the best known is probably Otter, but today we have very strong systems like Vampire, Ish, Pass, Prover9, etc., etc. And people also have worked on various more limited logic. So the logic used for formalization of mathematics are the sort of most expressive ones, like type theory, set theory, high order logic. For automated theorem proving, the biggest successes were this first order theorem proving. And if you go even more limited, you get propositional logic there, for example, the Davis-Putnam or concept-driven close learning procedures are really superhuman today. So there are actually some mathematical results that have been reduced to them, and which people have solved thanks to very high performant superhuman solvers for these logics. So that these are logics like set, propositional logic, quantified Boolean formulas, SMT, UEQ stands for unary equational formulas, etc. So there is a spectrum of these formalisms in which people sort of attack mathematics and automated reasoning. Why would you do it today? So the successes, the relatively recent successes in sort of formalization and interactive theorem proving are proofs of the Kepler conjecture, which has been open for basically 400 years, and it has been proved by using a lot of computation in 1998. But then the proof was so big that mathematicians couldn't actually verify it. And because of that, the leading person, Tom Hales, who was responsible for the informal or standard proof, declared an effort to really verify the full proof on the computers. And in 2014, the project was concluded. I will say a bit more about it. And that there is a bunch of really high-profile projects like that, where people have taken one or two books, like graduate books in advanced mathematics, and really fully formalized it in proof assistance. So that's the sort of mathematical push. The interesting part of this is that basically all the technology that is used for math is also used for verification of hardware and software systems for the I would say the most like verified way of doing that. So people have really verified today compilers, like this concept project. It's a huge effort. Operating system microkernels like SCL4, again, a huge effort. Chips, transport system, finance system, cryptographic protocols. Amazon is now paying a relatively big group to verify, for example, the OpenSSL stack, so that the browser communication, browser server communication is verifiably correct and cannot be hacked. So the technology is sort of tedious, but it's getting more and more automated, and it's helping a lot of these domains to produce software and hardware that is provably bug-free, obviously under some assumptions that are integrated into the mathematical proofs of being bug-free. And then there are all these blue sky visions that I already mentioned, going back to Leibniz. John McCarthy has this great vision of objectivity and power of initiative. So he says, like, currently the society is sort of layered, and it takes a lot of effort for a bright Indian student to come up with a change to an American immigration policy. So what if we change the rules in such a way that if somebody has a pseudo proof, which is something like a formal proof, then the whatever State Department in the United States really needs to consider that suggestions by the bright Indian student, because there is a pseudo proof. So there is all sorts of visionary stuff, like how we could improve all of the society, not just the sciences, if we could do very strong automated reasoning methods. I decided to give you a small hint of how these things look. So many of you have probably seen this. So this is the proof, informally written proof of the irrationality of square root of 2. And I will not repeat it here, but you can sort of read it for yourself. And here is one way how to write that proof in a formal proof assistant called Isabelle Hall. So you can sort of see that the proof sort of follows the informal one. It's sort of reasonably similar. You have these keywords like assume and hence and then, etc. And you have the language for mathematical formulas, and you have some sort of way of justifying it. And when you say QED at the end, the theorem prover will sort of think hard for a bit. It will check the natural language structure or natural deduction structure of the proof, and check all the steps. And if all of this checks, then it will declare that you have really proved this theorem that you were proving. The big example of this is the couplet conjecture that I have already mentioned. So it's this most compact way of stacking balls of the same size in space, which has been conjectured by Kepler in 1611. Tom Hales proved it with a very long proof in 1998. The reviewers couldn't do the reviewing properly. They tried and they failed after some 4 or 5 years. So in the end, this was all done formally, about 20,000, 25,000 lemmas in all sorts of mathematical fields. And the formulas look like this. So for example, this thing says that if S is a polyhedron and C is the face of that polyhedron, then C is also a polyhedron. This took 20 to 30 person years. It was a multi-person project to do the formal verification. And with my colleague Cezary Kališík in 2014, we have shown that by combination of like machine learning and automated theorem proving methods, we can prove or hammer away, that's a terminology that has been introduced some time ago, about 40% of those 20,000 lemmas. So that's sort of like the first hint how much the sort of AI/automated theorem proving methods can be useful for these big verification formalization projects. To give you a bit of overview what we do today, like what are the various AI and machine learning combinations with theorem proving, typically like there is something that can be done on the high level. So for example, if you have a big library of theorems like these 20,000 lemmas in the FlySpec project, you can train some pretty standard machinery, some sort of Google search for telling you when you are proving a new conjecture, new theorem, what will be the useful lemmas or premises to use for that proof, because the automated theorem provers are typically very explosive. So if you give them too many facts, like 20,000 facts, they will typically very quickly flatten out and not prove anything. So that's a quite important and quite established field. The sort of low-level things that you could think of and that actually has started to work some 4 years ago is to do some sort of machine learning style low-level guidance of the automated theorem provers. So these automated theorem provers, they are really very fast, that they can do millions of steps within a minute, for example. And it's sort of an ambitious goal to put some machine learning guidance into them, because the machine learning systems are not that fast. So if the machine learning system costs you 1 second per one recommendation, then there will be a problem. But it seems that today we can really quite a lot improve even the sort of low-level operation of these automated theorem provers, and I'll give you some more examples of that. There are also like some various compromises where you are not advising the sort of very low-level system, but you choose some reasonable middle levels when you can, for example, tell it now do induction, but you are not telling it exactly how to do the induction, or now do rewriting, and you are not exactly, you are letting the low-level system to figure these things out. And then there are these sort of more AI tasks, like for example, theory exploration or conjecturing, is that when somebody gives you a theory, some axioms of a theory, you want to come up with interesting conjectures in that theory and prove them, or recursively start to invent what would be good lemmas to prove your bigger conjectures, etc. And a very interesting task is auto-formalization. So we give you a mathematical textbook written in LaTeX, and now we would like to translate it to a formal language like I know, Isabelle, Hall, etc. And verify that. And obviously we can use both the machine learning technology like transformers or whatever, but then we can also use the semantic technology like type checking, theorem proving, etc., and combine them in like various feedback loops. So that's the overview.
Yeah, we don't have a huge amount of time left. I see you've got rather a lot of slides left, so maybe you can move a little bit faster.
Okay. The main technology that is today using automated theorem proving and AI for assisting people who do mathematics are hammers. So this picture sort of says it all. So you have a proof assistant like Isabelle. You translate things to some weaker logic, like first level logic. There you employ some automated theorem prover after you have done some sort of premise selection using the AI tools. And if you find the proof, then you sort of ship it over back to the more to the stronger formalization. So these tools, like I said, had something like 40-45% by 2016. Today, by deploying the internal guidance of these systems, we can do about 60%. I will not go through more demos because I'm out of time. I will not go through this. I will give you one example of the sort of reinforcement learning loop that we are doing. Like this is quite recent. So we take an unaided, unguided best automated theorem prover called eProver, and we put some sort of machine learning guidance into it. So initially, and we run it in something like 60,000 problems, mathematical problems. So initially, the unguided system can do something like 15,000 out of the 60,000, and then we sort of train some sort of graph neural network or some sort of other fast classifier that we put into it. And then in the first iteration, it improves by 10 or 40%, depending on how we do that. Then we relearn on these new proofs. And we do it again. We plug the sort of stronger classifier into the system. And we do this about 6-7 times. And ultimately, we get a system that is about 70% stronger than the initial system. So in this sort of way, we are sort of creating some sort of combinations of learned classifiers and the automated theorem provers that really improve efficiently on the unguided automated theorem provers. Because the people are interested in GPT, here is one experiment when we ran GPT over a lot of mathematical texts. So this is one quote unquote proof produced by GPT. So what you can see is that the proof is sort of syntactically correct. It sort of type checks. It also has quite decent natural deduction structure. But if you really understand what it's doing, then you will see that eventually at some points like this line and this line, it produces a totally implausible and incorrect mathematical statements that cannot be proved and that are basically useless, even if they sort of were provable in that sort of proof context. So it's interesting to sort of explore the capabilities of these, for example, language models or graph neural networks in this context, because we can very clearly see what the systems are capable of and what they are not capable of. Last thing, because I'm running out of time, the neural formalization seems to be quite doable using these sort of language models, for example. So what we did about 3 years ago is to take about 1 million informal to formal pairs and train at that point recurrent neural networks with attention to them. And this is how the data looks. So this is sort of the LaTeX thing. And this is the LaTeX, and this is the formal thing. And this is showing you the gradual trained system producing output on the LaTeX input. So basically, this is the LaTeX input. This is the formal correct output that we would like from that. And you can see the various snapshots of the system as it's being trained. So initially, it produces total garbage because the system isn't really trained properly. But as you go further and further, the snapshot 7000 is basically what you want. So in this sense, that there is quite a bit of hope that the neural systems combined with some sort of type checking and theorem proving will be very useful for this very interesting task of putting mathematics from LaTeX or textbooks into the formal proof libraries where we can really use these theorem provers and other stuff. And this is the last slide. So I would say the big challenge today is to learn complicated symbolic algorithms, and basically we don't have much, in my opinion, in that direction. And I would say the sort of language models are, if I train them on complicated algorithmic or reasoning tasks, they really fail quite badly. The graph neural networks seem to behave better. There are various challenges, like prove more and more of the mathematical theorems, which are harder and harder in all these large mathematical libraries. So I did some predictions and bets about 7 years ago. And actually the sort of nearest one we managed to do in 7 years, like this 60%, going from 40% to 60% on the Mizar corpus. So it seems to me that it's quite safe to say that in, I don't know, maybe 2-3 decades, we will really have relatively strong theorem proving advisors and strong auto-formalization machines. When we will get to things like Fermat is unclear to me. Like there was a discussion about it recently on the Foundations of Mathematics mailing list, and my estimate is that the human formalization could be done by 2050, and the fully automated proof, it's depending how you define it, could be done by 2070. So that's it. Thanks for your attention.
Thank you very much. We're running a bit late here, but so I think ask anybody got a specific question for Joseph? Ross.
Yes, so I said at the beginning of my slides, I didn't think it was clear what mathematicians are actually doing. You seem to equate mathematics with proof, but you know, that's not the whole of mathematics. Isn't the hard part making the interesting conjectures, which you then want to prove?
Yeah. So that's the part that I skipped. You are right. Like making interesting conjectures is definitely a very interesting task, and it relates to all these other tasks. Like, for example, coming up with interesting mathematical objects in general. Like, for example, proposing an interesting algorithm. Like maybe so. For example, today we can see that the trained system can really integrate and differentiate and do matrix multiplication, etc. Also, so it sort of learned how to combine the rules, and you could say that it's some sort of beginning of some algorithm, but sort of spelling out that algorithm precisely based on what your sort of neural network tells you to do with the sort of mathematical content is non-trivial. So all these things like proposing an interesting mathematical conjecture, interesting mathematical witness inside some proof, and interesting algorithm, they are definitely the very hard ones. Some of that is sort of not really necessary if you look at it from a strict logician's point of view. So because we know that, for example, the axioms of ZFC of set theory are complete, what is happening to us when we are getting bigger and bigger proofs is that basically the machine learning methods that we have are guiding the synthesis of these objects. So for example, if you are doing some geometric constructions, the the sort of guiding machine, if it's really, really good, will sort of guide you by the application of the axioms that you have to construct the required objects. And it's getting better and better in that. But obviously you can go to that goal from some other direction, right? Like what I'm here showing on the slide is that GPT-2 proposed some generalization of an existing theorem, which was actually true, like it went from finite groups to arbitrary groups. And then sort of the mathematicians involved were able to confirm that this is actually true. So that's a very interesting task, like how do we, and how does it relate to the task of synthesizing the objects by the proof rules, right? Like, is the mathematician working in the sort of same formalism, or is he working in some sort of more higher level of formalism when the conjectures are somehow created in a sort of more higher way of doing that? Yeah.
I think maybe we should move on. I'm sorry to curtail that bit, but we will have opportunity towards the end for some more discussion. Thank you very much, Joseph, for a very impressive talk and showing the mathematics side, the theorem proving side there. So I think the final talk we have here is Joaquin, who is Eindhoven, and he's going to talk about a very important aspect here that we've been seeing all these AI being applied to science, mathematics, and so on, but because it's very important to communicate this and spread good practice, and spreading good practice in AI for science through AutoML it's the topic of Joaquin's talk. Over to you.
Thank you.
See where you are on my screen.
Are you seeing the right screen? Yes, all right. Good.
Yeah, all looks good.
All right, thank you. Yeah, so I'm Joaquin Vanschoren. I'm professor at the Eindhoven University of Technology. And I'll talk a bit about AutoML and automated machine learning and how it can help with spreading good practices in science. So to break this talk down a bit, I'll first explain a little bit why automating machine learning is useful. Then a bit about how it works, so we have a better concept of what we're dealing with, and then I'll talk more about the future and open challenges. So first, what are the high-level goals? Well, one of the most important goals here is to democratize machine learning, to allow many people to use machine learning in many, many different ways without needing to have a huge amount of prior experience. So they can focus on the things that they're really good at and offload some of the more complex work to automated systems. So I'm added this example because it often came up in this workshop about how we can solve really hard scientific challenges. And oftentimes to do that, we need a large team of experts from different disciplines to work together and invest a lot of time and compute into finding the solution. The goal of AutoML is basically to enhance experts by adding automatic machine learning tools so their work becomes much easier and they can develop new machine learning models and new solutions much faster. And so as came up several times before, even today, is we really want these expert AutoML teams, right? We often typically don't want to have an AI doing everything for us, but we want to have these centaur teams, these teams where experts and automated tools can work optimally together. So first of all, why is machine learning so labor intensive? So why does it typically require so many people to work together, and why can't the average scientist build very complex models very easily? That's often because machine learning pipelines and models, they have a huge amount of possible options, especially if you go to deep learning, there's a huge amount of possible things you can do. Some of which are known, some of things are not known and will have to be further developed. And there's a lot of implicit knowledge needed. So first of all, when somebody gives you a scientific challenge, you first need to spend a lot of time in collecting the right data, cleaning it, preprocessing it, finding features, selecting the data, selecting the features, and so on. That already requires a huge amount of options, right? There's so many ways you can clean and preprocess data, many data sources you can sample from. So that already is a lot of work. The next thing, you need to choose the models. So maybe you are happy with a Bayesian model or a Python machine, maybe you want a neural net. And say you want a neural net, then, well, you have to design these complex architectures, right? This is, for instance, the inception network. You can see it's very structured, but it's also very complex, right? So it doesn't just manually fall out of the sky. You need to think about how to design these architectures. And as you can see, there's lots of different options you have. For instance, how many layers do you want? Typically, you want to have modules that repeat themselves. You have different kinds of operations, like this convolution, max pooling, and so on. And you need to string them together in an optimal way to find a good solution. And then another interesting thing that comes up a lot is that, well, we learned that we can actually reuse these models, right? So when we pre-train these models on large data sets like ImageNet, we can typically, or large corpora of text, we can typically reuse them into other solutions, right? Then we talk about transfer and continual learning, like few-shot learning, zero-shot learning, and so on. Then the question is again, okay, so which algorithms, which architectures should you copy from? There's a huge question in whether you can do this reliably. If you have many options, which one should you use, and how much do you still need to fine-tune and train those models afterwards? And all that depends on how much data you have, how much compute you have, and so on. So that, again, lots of questions that you need to answer. And so in all of this knowledge is typically very implicit. A lot of it is a gut feeling about what may work, what not work. There's a lot of insight as well, but oftentimes we still need to go through a lot of trial and error to see whether something works or doesn't work. Right? So the question here is, can we automate this process? And can we share all this implicit knowledge that is needed to build these solutions? Right. Another question is, well, another reason why we need AutoML is to build robust autonomous systems, right? So imagine you have a situation where you don't have humans involved. You still want these systems to be able to stand their ground, learn by themselves what to do. And yeah, that requires that requires that there is knowledge about how we build these systems that can be readily used by automated systems. And just to put that in a bit of a context, I'm not saying that AutoML will solve all these challenges. It's just a very small part in the wider challenge. There's an interesting post by Amit Tawalkar, where he compares it to the evolution of flights, where long ago we had the first Kitty Hawk, or the first autonomous, controlled flight. It then took a number of years until we had cultural acceptance, but then only the elite could actually fly. And now we have, of course, democratized flight. And if you look at AI, I think we're somewhere in the middle right now. So we have the first good AI systems, but it's not for everybody. It's not always easy for anybody to use AI systems, with some exceptions, right? So there are some pockets where it has become very democratized, like these language models and so on, which are already very, very useful. Still, if you look at AI as a whole, there's still that's just the tip of the iceberg, right? There's a whole lot of applications where AI is not accessible to a lot of people. And if you look at what happened in flight, that last step towards democratization requires a lot of efficiency improvements, automation, safety, and a lot of engineering as well. So to democratize AI, automation is one aspect of this, but also equally important are efficiency. These systems must be very efficient. They must work in situations where there's very little data available. We may even need special hardware before we get there. And definitely safety is very important. So we need to think about explainability, fairness, and cost analysis, which AutoML doesn't really solve. Okay, now how does AutoML work? So what we want to do is challenge the current module, where you have a group of scientists and they develop models by trial and errors. They follow they read papers, they follow their gut expertise, they try some models, they look, does it work or not? And then they, like Ross explained, make a new hypothesis, try something else, and then go through this manual trial and error process, which is very expensive and takes a lot of time and may often end up with models which are suboptimal because, well, we're limited in the number of things we can try. So we more often than not, we are likely to end up with suboptimal solutions. What we want to arrive at is this situation in where the scientist sort of explains the task that needs to be solved. And again, explaining the task is a very important step that AutoML doesn't solve. It needs to have a clearly defined goal. And then there's this AutoML system that then massively tries many things, then reports back to the human what worked, what didn't work. And ideally, these systems are automated, data-driven, of course, and they have some kind of memory. They learn across tasks so that when they see a new task in the future, they have some memory, like, okay, this looks like that task that I saw before, so I'll start my search by trying these kinds of models. Right? Or it could be something even more structured knowledge. It's like this is that kind of task, and so I should look for these kinds of models. Right? And again, these tasks can have all kinds of constraints. But by having this knowledge, by having this stored memory, learning across tasks, these AutoML systems allow effectively for even people which have less experience to find models effectively. So even if you see a new task, you don't have to start from scratch anymore. These AutoML systems have learned over time what works, what doesn't work, and can effectively search more efficiently for good solutions. Right? So ideally, these systems learn across tasks and then transfer that to other scientists. Well, that knowledge then becomes like a hive mind, like a common knowledge of what works, and then is applicable to everybody. If you look at what drove progress, especially in the computer vision, you can see that for the first 5 years, we had a lot of manual architecture design. Like we discovered things like normalization and skip connections to be able to build deeper and deeper networks. We developed optimizers so we can tune our learn rates effectively. We learned to build networks which are not like one block, but they consist of repeated cells that come back often in the same architecture. And all these inventions led us to near human performance in for ImageNet. If you look at the last couple of years, a lot of the improvements came from automatically designed architectures. Right? So these are architectures like NestNet and AmoebaNet. So these use AutoML techniques to fine-tune those models further and get better performance. I want to preface that here because this was only possible because we had prior knowledge about systems, right? So, and what we do, we often encode things that we've learned over the years into these AutoML systems. So the AutoML systems themselves already have a lot of knowledge encoded that we as a community have found to be useful. And that way, it's also easier for people to make use of that information because these AutoML tools will use it when they search for optimal algorithms. There's already some kind of sharing of knowledge happening there. To quickly break this down into so AutoML systems, what kind of things they solve? Well, first of all, we need to define a model search space. So this is the space of all possible models that we want to search. These are things like cleaning operations, what's the architecture of my neural nets, which layers are possible, and so on. And this basically defines a whole complex search space. When you've defined that, then the question is, okay, how do I look in that search space for the optimal architecture? We can look at things like evolution, Bayesian optimization, reinforcement learning, to basically learn how to find the best architecture in that space. And finally, there's meta learning. How do we transfer experience from previous tasks? I typically don't want to start from scratch. Granted, a lot of AutoML tools do start from scratch. That's often for research purposes. In practice, in the future, hopefully we don't have to do that. We can leverage what we've learned before. So one way to do that is, for instance, transfer learning. So we can reuse architectures that worked well before, things like representations for images, for text, that we can just copy, and then starting from there, design new models that address specific scientific goals. And also warm starting. So when we see a task which is similar to what we've seen before, we should warm start from there. Right? We should not start from scratch again, but again, start from the models that worked well before, and then from there, fine-tune that to the problem at hand. One example of such a model search base, just to give you an idea, I won't go into details because it's quite extensive and there's a lot of research here. But what many of these systems do is they have sort of like what we call the backbone. So it's like a fixed architecture. And so you can see this as blocks. These are tensors. And then between those blocks, we have operations. And the operation can be like a convolutional layer or max pooling layer, or it can be nothing, or it can be something else. There's some work in where you even have an infinite number of options here. Okay. And what you then do is, typically you want to search this page efficiently. And so originally a lot of work was searching all possible options. Every option is then like trained, and then after it's trained, we get a result back, and then we try the next thing. That was super expensive. So what many AutoML tools do now is they search the whole space simultaneously. So it's like one training operation where you try to basically you give every of these options a weight, and then you train those weights together with the weights of the neural connections. Right. So, and this principle is also called weight sharing. It uses bi-level optimization. And what it effectively does is you learn the weight of the neural net and the architecture at the same time. And that's massively more efficient than other ways of doing it. Right. And another very important thing is compositionality. So we typically don't learn this very complex architecture from scratch. We simplify the problem by breaking it down into smaller blocks. We learn the smaller blocks, and then we combine those smaller blocks into more complex models and then get a better performance. Okay. How do you then optimize those things? Well, there's different things you can do. One thing that often comes up is evolution. So you can start with very simple models, like on the left here. So this graph shows time versus accuracy. And in the beginning, it tries very simple models, which don't work well, and then it gradually adds things. Like you evolve the network by adding layers, removing layers, changing operators, adding normalization, adding skip connections, and so on. And you kind of evolve them. You also do things like mutation and crossover. So if you have a good architecture, you can cut it in half and combine it with another part of an architecture that also worked well. And that way you can evolve towards more better and better architectures. Right. And then again, there's a lot of things encoded in here. So things that are useful are often discovered and then reused later when you design new architectures. So again, learning from scratch is super expensive, but what you want to do is when you have a new problem, you don't start from scratch, but you start from all these models that you think are good, and then you further evolve them into your final solution. There's also interesting work here by Google a couple of years ago called AutoML 0. So there they actually trained from scratch all the way, which is not so interesting for real applications, but it's interesting because you can see that a lot of things that we know, like linear models and value activation functions and so on, they were rediscovered through evolution. Right? So it is an interesting lesson here that we can actually discover new things, and when those things prove useful, we can add them as a building block, and then the AutoML systems can reuse them and learn more complex things. Another thing we can do is spatial optimization. So here again, so say you have a new task, what you can do, you can look at, oh, this task looks at that task, so I will try some models that work well, and then you evaluate those models. What you see here on the right here, say that the x-axis here is your that's your space of all models. You try some models, you see how well they work, and then you infer from that. You build a model based on those results, and you infer, okay, if this works and that works, or this works and this works better, then maybe that works even better, right? And so every option becomes a dimension in the search space. You then learn from the things you've already tried, and then you predict, okay, what's the next interesting to try? And then you typically do something like a combination of exploration. So you try things which you think are promising, but also, well, you want to explore at the same time other things as well. And this was, for instance, used to optimize the solution for AlphaGo. So it's a very useful technique. This is a visualization of that. So maybe you should focus on the bottom left here. So here you can see that these techniques, this is only 2D, of course, but they search the whole space, but they put more effort into the models which have the highest performance. Those are the yellow parts here.
Nice. Maybe you could move towards the conclusion.
Yeah, so the last thing is reinforcement learning. I'll skip that. And towards the future, what still needs to be done a lot here is learning systems. So systems that learn over time, so that if you have a new task, you don't start from scratch. You can build on millions of prior trials before. You can do things like simplifying the search space. You can warm start from solutions which worked well before, or you can even build these huge meta models, which in themselves encode all the information. Google had some interesting news there a couple of weeks ago, where they had these huge models, which basically encode all the information into one giant model. Yeah, finally, if you're interested in that, we have this platform called AutoML, which allows you to store lots of models and encode knowledge that can be used by AutoML systems. And yeah, like I said, there's lots of open challenges. One important thing is human in the loop. How do we, because many systems currently, they just give you a solution. But what you want is to have human in the loop that continuously either directs the AutoML system or let the AutoML system itself ask questions about what the human thinks should be done. It should ask for help. It should self-assess whether it's doing something trustworthy. Are these models that's developing, are they useful? Or maybe they should be interpretable. Maybe there's something else that they need to do. Maybe they need to detect biases and so on. Things like real-world constraints, time, efficiency, and so on. And ideally in the future, we'll have AutoML systems which really operate like a lab assistant, like a smart AI assistant, which you can talk to, which gives you solutions, but you don't have to do everything yourself. Thank you. We have a book out if you want to learn more about this. That's it. Thank you.
Thank you very much for an excellent talk. Maybe again, just a time for one very specific question before we go to the more open discussion. Anybody got a, okay, Sašo.
A very quick question. Now the focus of AutoML seems to be mostly on automation, but I believe there is a lot of value of actually contributing to understanding machine learning and when, what works best when. Mm-hmm. And that aspect somehow is getting lost, I guess, in the spirit of automating the architectural search for neural networks.
Yeah, it's a good question. So there's two things here, right? So one thing, like what works when, that's something we can already sort of answer when you have a specific question. So if you have, like, if you specifically know this is a challenge I want to address, you could look at what similar tasks do I know that also worked well. The other thing, like discovering new things, what we often see many times when we do any kind of meta learning is that we see that AutoML systems rediscover things that we already knew. Like there's even work that like rediscovers things like atom optimizations. And there's a lot of things which are implicit. So we see it works, but they're encoded in like recurrent neural nets. And so we sort of have to start reverse engineering to try to understand why something works or not. And that's still a very open area. Gary?
I already put my comment in the thing, but I'll kind of read it out loud. It's interesting to think about what kinds of things are in the scope of what can be learned and what aren't. So the optimization functions are actually quite naturally learned by these systems. And representational schemes, like the ones that AlphaFold uses for how it represents a protein thing, you're not going to be able to do with this system, you know, starting from pixels and so forth. And
so, yeah, short answer is no. So we still, But the nice thing is that when you discover something new, you can add it to the system. So there's an easy way to share your knowledge by adding it to these AutoML systems, and then they become available to everybody, like things like attention, and it was a very interesting developments. The other thing I wanted to add was, sorry, I forgot. But yeah, there is some work that, so alpha AutoML, so AutoML 0 goes in that direction, but there's also other work like XD operations, where you, instead of saying like a convolution is a possible thing to do, what they say, well, a convolution is a special case of this complex matrix operation. And then they say, okay, well, if that's the case, then every version of this matrix is a possible operation, right? So you can sort of replace convolutions with these matrix operations, and then you have this whole big space of things you can rediscover. And therein, possibly there lie interesting things that we can, new things that we have discovered, but at the same time, that means that you open up a whole new search space that you need to search, right? So
I think good science is about knowing which search spaces might be worth pursuing.
Yeah, so there is something in there, like they do specify this, for instance, in terms of matrix operations. And there are some things like certain matrices have certain properties which are nice, and there is some little bit of work on like foundational work and like what makes sense, what doesn't make sense. But yeah, I think at the one hand, we'll discover some new things with AutoML that we haven't seen before, but at the same time, some things we will never discover with AutoML, and we need humans to put them into the system.
Okay. I give the last word for this part of the thing to Alistair, or we move on to the more general discussion section.
Yeah, thanks very much for this fascinating presentation. Maybe two sort of points. One is, I mean, one of the reasons why we're interested in OECD, in particular in this question, has to do with the policy issue of there being a skills shortage of in AI and its various subfields. And so we're trying to kind of understand what is the opportunity for helping to close skills gaps using AutoML. I just wondered, like, are these systems good enough now to be kind of value-adding complements to scientific teams? Or, I mean, maybe to do good scientific work, you just require teams where the AI contributors maybe are not the top flight AI researchers, but they know enough. And so maybe you could just give me your reaction to that one thing. And then related to that, because the skills issue is so important, and Ross began by making the point that so much AI talent is actually being kind of drawn off into socially trivial work in advertising, revenue maximization in large corporates and this kind of thing. Is there, do you think, some sort of underinvestment in this particular area of research? Is it lagging, or is it just keeping abreast with everything else? Thanks.
Yeah, thank you. So one, about the skill gap. I think the main thing is AutoML. So AutoML systems, they do still require some knowledge, right? You don't want to, like if you're not experienced in machine learning, you don't want to blindly take an AutoML solution like a model and then apply it blindly. You still need experts to, not experts in like architecture design, but experts who know basically what to look for in a model to see if it's trustworthy, and that are able to apply it and test it effectively. But the main thing that AutoML does is it just massively empowers these people. Like people who are sufficiently expert in AI, they now don't have to waste weeks tuning models. They can just offload that and put their time into the really important things. So that's one thing. So you will need fewer people because, well, those people are much more efficient, but you still need training, of course. But underinvestment, I think, like Ross said in the beginning, a lot of these tools, a lot of development happens in big companies, and yeah, that's great. But you often also want like every scientist to have access to this information. And these systems are not always already quite easy to use for everyday scientists. So I think there's still a lot of work needed there, especially if you try to, like, one thing we experience all the time is when you try to run these AutoML systems, they oftentimes break because there's something funny in the data, right? And because the systems are not robust enough. They're not robust against, for instance, typos in the data and so on. So we still need a lot of investment into making these AutoML systems really robust and really efficient. Yeah.
Thank you. So maybe we can now move to the sort of more general discussion of the whole day. We have highlighted the agenda as some specific discussants, although many of them have already been making a contribution. But maybe I could ask Hiroaki for your view on the range of topics that we discussed this afternoon.
Yeah, well, thank you very much for inviting me for this panel, and I enjoyed all the talks, in the sessions, really interesting and then very insightful. And, I think, that the issue of creating a robot scientist or the AI scientist, requires a little bit of a change in the perspective, so to speak. I mean, a lot of effort has been, spent on creating the ML system or the AI system more broadly to discover the specific things, and of course, that's very important. I mean, we need many of them, much more, and some of them, be groundbreaking, like AlphaFold 2, and that's actually really groundbreaking in terms of biochemistry, and it will be a game changer in that domain, and it's really need to congratulate Demis Hassabis and his team for accomplishing that. At the same time, that is the kind of a system we defined what need to be done. So we are defining a task and then we're training it, and for the to be AI science to be able to discover things, the major discoveries, it is not sufficient to be able to discover something which is defined. And I think AI scientists need to be able to make some a selection of topic, and then they get the strategies and a choice of the analysis pipelines, and then a choice of the experimental procedures, and then there are some anomalies and deviations, and they have to be able to fix that. And that is a more broad, highly autonomous competence that we require, and that is actually something we envisions towards the end of the day, I don't know, 1 decade from now or 2 decades from now, when you say this is the highly autonomous AI scientist, that it's not single task, many tasks that can be flexible. Okay. At the same time, I think we can have a low-hanging fruits. Okay, we don't really, starting not really expecting that level of autonomy, which is very high, and that's obviously very high. Okay, in a biomedical area, there are many, experiments or many knowledge that has not been confirmed. For example, when you do the yeast biology, which Ross actually done the part of that. And we haven't identified all the molecular interaction under different conditions, but we can actually, in postdoc or even the grad student, to be able to identify a specific molecular interactions, maybe 1 or 2 of them per year, for example. But we have thousands, the millions of them, and we cannot do that. The reason why we cannot do that is that sociologically, it's not possible for us to actually deploy postdoc to be able to do that. Some of the molecular interactions considered to be less important, and then it will be hesitant that you actually put one of your students to go for that, because with the students spending 3 years doing that assay, and they turn out to be really not that interesting in terms of a foreseeable time horizons. You kill the career path for this student. So because of that, we cannot really go to exhaust search all the possible molecular interaction, epigenetics, and messenger RNAs, and all that. We really have to have some kind of expectation. This has to be important. This has to be important in terms of based on our knowledge, our preoccupied conception. This is likely to be important rather than the, going to be important in the over the horizons. So like we are actually constrained by the, very typical, horizon problem in the AI, that our actually decisions and what kind of research to be made will be constrained by the knowledge we have and expectation level, what would be important, and that's actually within the horizon that we have. But of course, like over the horizon, some of the things which may not be important could be very important, but we cannot do that because of the if that's expected, that prediction didn't work. I mean, you jeopardize young researchers' career. So like at that level, we don't need very high level of autonomy. But we need a certain level of intelligence and an autonomy, because like any of those requires some sort of irregular things happening, and we have to be able to fix it. We will do it in the millions of them, right? So, but in that case, I think like we're gonna have like quite substantial game changer kind of machinery for the biomedical science, because the many biomedical science is we are bombarded by the complexity and then the size of the problem. Each of them may not be that difficult, but I guess the number of the knowledge we have to verify and go on an experiment is gigantic, and then it's contextual, and then it's sociologically impossible. I mean, that's why that has not been done by the human hand. So I think like we have like an immediate value of that. Then the question is, well, we're doing that, we may not lead to something very important. Okay, it's like something will be important, that actually our expectation based on what we know, and there's no guarantee our a priori assignment of the level of expected importance of the specific knowledge may not be actually hold. So like some of the things that may not be, we didn't consider that important, could turn out to be extremely important, and that that's why like fortunate accident or like those serendipity comes in. We consider those as serendipities as that's all like a fortunate accident, because that region of the parameter space search we didn't consider that important. That's why we haven't tried to even search that. And then accidentally we're go into that parameter space, and it turned out to be very important. And the reason why that actually turn into the big discovery, only by accident, is our preconceptions exclude the importance of that parameter region. So like if we actually got to the a machine to be able to have like a broad parameter space, of course like we're not gonna be resource constrained, so we cannot really do everything. At the same time, we will remove the sociological constraints, because that will be done by the machines, not by humans. So we don't have to risk like career path of the any of the student or the postdoc that will be involved. So but that would be like I think like a really big game changer in terms of the biomedical science. I mean, of course, like a human genome project or like a gene DNA chip and then the microarrays have done that in genomics domain. I mean, before human genome, before microarray, every gene expression has been done by us like a very labor intensive process. Now we can just put the samples, and we get like all the time as expression change of the genome wide. And that became like a big game changer in a biomedical science. That something we can do in our omics scale on a high throughput level is limited, and I think we can really push that boundary, moving things forward. Okay, now the other aspect is I don't think like we need to expect the AI science to discover everything. That would probably not be interesting, because then there is no joy for science. I think we should reserve something for the human to be discovered. But at the same time, what the AI scientists may discover could be something very different from the human expert. Of course, like the overlap, but like just like an example I gave, like those exhaustive saying and building up from there, it's not kind of thing human is not good at it because of the the complexity of issue and the career path issues. But we may actually have like an AI scientist discover quite substantial new thing from there, and some of them could be really groundbreaking. Okay, now so I think like a type of the science which will be carried by like robot scientists, AI scientists, could be very different. So like what I'm saying is, you know, through the Nobel Turing Challenge, for example, like we're gonna actually create like a new form of science, you know, alternative form of science. You know, it just like you know, we're not really. I don't think we're gonna try to mimic a human scientific discovery process. I mean, it's many research in the past, scientific discovery in AI, or like a cognitive science research or science philosophy of science research, trying to mimic the trace how human discovered. And I don't think we should do that. I mean, you can do that because it's cognitively important, interesting, cognitive science. But if we have to have like AI scientists, I think we should take a different approach. I think it's very interesting analogy. Was like this is like a airplane example. You know, what we're trying to when we try to understand what the human scientific discovery and then try to mimic that, it's just like we understand how the bird fly. And try to actually create the machinery that actually had a wing and then flip them, you know, and that doesn't fly very well. I mean, it's okay, but like, you know, the evolution for the airplane is we decompose the fly to be thrust and lift. And because like we get a fixed wing and we got the engine to that. And that was actually a complete redefinition of the flight from the engine. So what we should aim at an AI scientist is a decomposed essence of AI discovery, you know, scientific discovery, and decompose that, reassemble that, and form something different, you know, create airplane, you know, not trying to create like bird. You know, so that will probably going to have like quite substantial impact. I think we can fly much far using this kind of machinery, and that's kind of intention behind Nobel Turing Challenge. That's what I'm thinking about. We should really going for this. And so like that will be very different. One more thing about like a Nobel Turing Challenge is that people might consider like a Nobel committee will not give award to the AI. Obviously, but that's Nobel's the will says it's given to the persons. Okay, you know, depends on how you define the persons. You know, general consensus is person given to the biological entity rather than the artificial intelligence. But you know, if you look at the Bitcoin blockchain, Satoshi Nakamoto is the guy who created one. As no one ever met Satoshi Nakamoto. You know, so like, you know, this is a simple blog post, you know, completely changing the financial world right now. So like if Nobel Committee on the economics have to give an award to the cryptocurrency, they have to give it to Satoshi Nakamoto. Very obvious because we invented the whole thing. But only reason we believe this is not artificial intelligence is we all believe AI is not there yet, you know. So like, you know, and of course, like even if Nobel Committee didn't really give an award to the AI, you know, if they actually internally get the alert, you gotta watch out because some of those author could be AI, and it will be shameful for them if they mistakenly give it to the award to the AI rather than the human. That would be embarrassing for them. If they start taking it seriously, I think we are winning the challenge. And of course, like I was invited to give a talk at the Stockholm multiple times. And then some of the front rowers has been the committee. And so they knew we are challenging them. And they like that. And for example, like president of the Karolinska Institute read my paper on the Nobel Turing. And then he came to me and said, this is a great idea. I like that. So like, they like that. So I think this is very interesting. We expect a healthy interaction with the committee and then how we're going to transform the science to define the alternative of the science. Okay,
Thank
that's
you.
my comment.
My guess is that the first place the AI will start to inform and possibly replace the Nobel Committee. And then
yeah,
it's clear that that's
so we have to actually see like you know, who's on the committee, the AI.
Well, the world does not say who has to be. It says there's the members of the Swedish Academy. Well, they can solve that problem. But I think that's it. Thank you. It's very interesting observations there. Maybe I could ask Bart to also have give some views on this overall area. what we've been.
Yeah. So so overall, I'm very excited about this area. It's one of my favorite areas in AI, scientific discovery. I see it actually more. So I see the great examples of AI having already made interesting contributions to scientific discovery. AlphaFold, for example, or some theorems that have been proved interactively, or even that are interesting. But I think scientific discovery also reveals sort of our shortcomings still in AI. And to me, the best example of that is the role of knowledge versus data. And actually, there's a great book by David Deutsch, The Fabric of Reality, and he really emphasizes the difference between knowledge and data. And he actually starts off by saying, when he grew up, he was always told, "Oh, there's so much knowledge in the world, you can never even read all the papers anymore and understand everything that we know nowadays." But he actually challenges that. He actually says, "No, the beauty of Einstein's theory or of Newton's work is it summarizes incredible amounts of data in an understandable way for us, and that is what science is about, is taking incredible amounts of data and making it in models that we can understand." And he actually says, in some sense, we understand the world a lot better and a lot more than we ever did, even though there's so much data out there. So now, as an AI researcher, I think we're still very poor at dealing with knowledge. And knowledge also has because it has a very symbolic, a very, literally symbolic nature. Mathematics, mathematical language is, of course, very powerful. And I'm thinking more of physics, but also chemistry, where formal language is very important. And it's a cumulative body of work. And it builds on previous concepts and on previous ideas that have been developed, and I think our AI formulas are still very poor at that. And one example was mentioned earlier on. If you take GPT-3, it was trained before COVID. So GPT-3 doesn't know anything about COVID, and you can't ask it anything about COVID. Of course, a human scientist, you can say, well, there's this new coronavirus that has been discovered, and it's contagious. It spreads possibly this way or that way. Immediately, a human scientist integrates that in their own knowledge of the world, and COVID isn't a strange term anymore. But with GPT-3, I actually don't even know what you would have to do. You would have to add thousands of articles about COVID or hundreds of thousands of sentences about COVID to get at some idea about COVID. So these data-driven approaches, to me, lack this cumulative capability that level representations have. And now, so as an AI researcher, I find that I welcome the challenge, and I would just like to emphasize here is that for AI research, scientific discovery actually reveals some of the shortcomings of our work. Let me give one final example. I mentioned before in the chat briefly. I do work on automated theorem proving. It's actually I got into it, mathematical discovery using automated theorem proving, and I was quite surprised. There was also a great talk on automated theorem proving, but it's mostly interactive theorem proving. That's human-guided theorem proving. I'm interested in, I give you the theorem proof with Peano's axioms, and now I wanted to prove Fermat's last theorem. How far are we? Well, as I mentioned, proving x plus y equals y plus x, you actually have trouble doing that fully automatically at this point. You can get it done if you give it the right induction hypothesis and you give the statements in the right order. You can get a theorem proof to do that. But going from commutativity x plus y equals y plus x to Fermat's last theorem, that's a long path. And if you can't get that first step done yet, there is exciting work to be done. So I see scientific discovery partly as revealing some of the shortcomings of AI, and I believe we're going to make a lot of progress, in part thanks to deep learning, but we should not think that we're that close to it. That's my comment.
Jeremy, may I make a brief comment here that relates to what Bart just said? So I think knowledge is very, very central, and there is no way around it because it's the primary product of the scientific process. You know, science is supposed to be producing knowledge, and we will have to have knowledge representations that both humans and machines are comfortable with. If we want to automate science, then the robot scientists will have to work with these knowledge representations in addition to the data. And if we want humans to be using that knowledge and to have sort of collaborative ecosystems between humans and robot scientists, they both will have to be comfortable with those knowledge representations and to work with. And I believe that's very important. So, but I will let Jeremy moderate further.
Well, I think I would just respect the things I've seen some quite amusing cartoons. The more data we have, the more we got to get rid of to get something useful. And of course, that's the whole way in which we get knowledge. But equally, our knowledge is not static in the sense that it's not just adding to it. You supersede it by new levels of abstraction. I reflect in my own discipline of chemistry. I have a set of notes that precede my undergraduate degree from the same place by about 40, 50 years. And they did a lot of work in 3 or 4 years, just as I did a lot of work in 3 or 4 years. So how come there's so much more chemistry we know now than then, and yet when the knowledge has advanced so much that you can explain things in a time so we can still learn it. So things move on, and that we have to understand how that happens and what goes on. And I think, you have the sort of area of physics-based knowledge networks there, physics-based models, where I always object to that because it's chemistry-based ones are good. It's science-based models here. But actually, that's great when the science is right. But if you start constraining the data-driven system by science that turns out to be wrong, you talked about area of the parameter space. There are plenty of cases where it was absolutely known these parameters had to be positive, for example. And then it turns out metamaterials come along and they can be negative. Okay, both various things have to be both. There were whole areas of sample space that were not explored. And yet the fundamental equations show, oh, actually this is possible. And then there becomes a question of how do you realize it? That wasn't simple. So I think these are really important areas. And by not imbuing some of these systems with the prior knowledge could be useful sometimes. On the other hand, other times it just wastes a lot of time. And I think the points we've made about accidental discoveries. Yes, accidental discoveries when recognized as the right sort of outlier. But I have to admit that there are plenty of cases where accidental discoveries, we found them really interesting, and then we spent a year looking at them and it turned out they were not interesting. And that's the same problem as encompassing the whole space. But that's even worse. We thought we'd found something, turned out to be something else. Okay, that happens. Maybe Anthony, you'd like to give your view on these overviews.
Yeah, thank you very much. Difficult to add to the cornucopia here, but I have a couple thoughts that might be worth thinking about. One is, where's this going? What do AI practitioners do N years from now? And we've been asking this question for a long time, but it seems to me that the second derivative has shifted quite a bit, and we should ask that question maybe more vocally. So it seems to me that the AI practitioners of the near future will be more like the clinical practitioners of today, where the systems that we're trying to interact with in the real world, I'm not necessarily talking about a specific vertical part of research, but in the think about anomaly detection or fraud or trying to understand shifts in sentiment in the context of disruption. All of these things are inherently nonlinear problems. You can't just look at longitudinal data because the future doesn't look enough like the past. Does AI have a right to play in that field? I say yes, but as a partner, not as a spirit guide, if you will. So we have to learn to be more clinical, to have a hypothesis, to have a differential diagnosis, to use some sort of AI method that we've chosen on purpose, or ensemble of methods that we've chosen on purpose to intervene, and then test a reaction and then repeat. So it's not push button, get answer, move on. It's more of a collaboration. And this is why I say often that we need some new words. there's no intelligence here. It's a lot of it is math. But our intelligence, I think there's definitely a place for it. The second thing I would say is, if I ask what's the role of the AI practitioner in our very near future, what's the role of AI in our very near future? And I would like to, as a human being, say I'll never report to a robot, but Outlook will tell me go to a meeting, or the GPS will tell me to turn right or left, and I do that. So to some direction, I'm already taking guidance from robots or bots or whatever you want to call them. The question is, how much of my human volition am I willing to give up, and what does it allow me to do instead? What do I do with that time? And can I ask better questions? It seems to me that if we address these two things, what is the role of AI in the future, and what is our role with AI in the future, then that leads us to asking new questions, better questions. And that's the essence of scientific discovery. So I don't see this as a versus kind of conversation. I see this as a, what are you going to do with this abundance of data and compute power and AI? And I hope the answer isn't, better advertising. Like, of course, there are people that need to do that, and I'm not saying there's anything wrong with that field. But I think it's been said several times here that that's the bulk of where the applications have been so far, have been hyper commercialized to a very small space. I hope anthropologists don't look back at this and say that's all they could do with it.
Thank you, absolutely. Well, I'm sure we can all do something with it, but on the back of, we know what drove the internet shopping. And we may not all want to avail of those facilities, but exactly, and at some level that means I can now buy my my opera ticket or whatever online. Great, you have to take advantage of the systems that are being paid for by other people. So let's so Sašo, you already indicated some views of the overall here.
Yes, I'd like to add another line of discussion. I liked a lot that in this afternoon session we also had mathematics represented, and also the talk by Joaquin. It was really about, in a sense, automating part of machine learning, AI, computer science. I like to view this more as more broadly as the formal sciences. So there is a lot of potential for automation and making progress by using artificial intelligence, because to a large extent things are already formally represented. The only thing is whether we have lots of these stored, and this is in a way also a question to our speaker from the Czech Republic about Theorem proving how much of mathematical knowledge really is formally represented via ontologies and in databases, because I feel there is a lot of potential there to demonstrate the power of artificial intelligence.
So thanks for the question. I think this is, I'm almost tempted growing exponentially today. I don't know how much I'm exaggerating when I'm saying that it's growing exponentially, but the very large formalizations that happened in the last decade, like the FlySpec project, the other theorem, these are really like graduate PhD level, sometimes research level mathematics, like the Kepler conjecture is basically new mathematics. Very recently, there is a relatively new interactive theorem prover called Lean, which, by the way, was recently endowed with $20 million by some cryptocurrency guy, because he saw that it really attracted like the top mathematicians, and Peter Scholze, who has the Fields Medal, basically had a newly created piece of mathematics about which he wasn't sure whether it's correct. And his colleague in Bonn has fully formalized it, and Scholze said about it that this is really surprising to him, and that the mathematicians are sort of jumping on it quite a bit recently. So to answer your question, I would say most of the bachelor level, maybe even master level mathematics is today like fully formally expressed in these several systems that we have. And there are, I would say there is quite a lot of PhD level mathematics also fully formalized. and now there are these forays into various parts of mathematics. And I would say there are two very interesting effects. Like one is the increased automation that we are getting by basically learning from the proofs that we have and providing stronger and stronger support to the people who want to make the next proof. And we are very useful in sort of filling bigger and bigger gaps. So they are more and more efficient. And the other thing which really seems possible today, and I wasn't so sure about it 6 years ago, but today I'm much more sure about it, is that the systems that translate, for example, LaTeX written textbook into the formal code are becoming really better and better, and you do not need too much for it. You need, like I would say, I'm not like an uncritical enthusiast about deep learning, but some of these language models, they are pretty good at translation between, for example, natural languages. And if you add some sort of type checking and theorem proving on top of that and make some more feedback loops, then it really looks like a lot of the mathematics that is only expressed in natural language or LaTeX will be quite soon semi-automatically translated into formal languages. And there it will be in this very nice territory that you seem to like, and I definitely like. So I see I see quite a bit of hope in this territory.
Thank you so much. I would only like to add two more sentences. The other very nice message that is emerging here is the need for human robot or human computer teams that collaborate on science. In this respect, I very much liked also the presentation which was showing the language models as tools for scientists to do literature reviews, to generate hypotheses. And I think they are going in the direction of really working, joint work between human and robot scientists. And I believe that really is the future. Thank you.
Thank you. So, Gary, you've talked had quite a lot of questions as we've gone through, and been a big contributor to the chat. So you have the floor to give your views.
I wrote out my closing remarks. They're very personal. So I woke up before dawn today to join you guys. I had to get up at 5:30. The reason I did it is because I think that the potential to use AI for scientific discovery is the single most important reason to do AI. It's why we should be doing it. But I'm also very much in agreement with Bart about knowledge versus data and the limits of current AI. I don't think we're remotely close to realizing AI's potential for scientific discovery yet. I mean, we've done some, or especially DeepMind has done some really cool things, and we've heard some others today. So there's progress, but I still don't think we're close to that potential. So I want to close with some remarks about policy and what I think is a moral choice, and give you my own perspective. As some of you may know, I split my career between studying human minds and studying artificial minds. And so a question that I often get is, will neuroscience help us with the problems with AI? So I'm kind of famous for criticizing AI. And people are like, well, is neuroscience going to solve all the problems that you talk about? And my answer is probably not. We might get something from psychology, but right now we don't know enough about the brain to be able to help in the near term. There's this vast complexity that I think Hiroaki pointed out in his remarks. And so I think it's actually going to go the other way around, that we need to figure out AI in order to be able to figure out the brain, because the complexity is so far beyond any human to fathom. And so the question, I think, is whether we want to focus on AI for scientific discovery rather than advertising and so forth, which would require significant investment in AI areas that aren't currently popular, aren't particularly lucrative. And I'm talking mainly about reasoning over incomplete knowledge, partial knowledge, acquiring deep conceptual representations, and having better natural language understanding, deeper natural language understanding. I think that that's hard. It will require tremendous shift in resources. But I also think it might change the world through advances in domains like medicine and using biotech to help us with climate change. So I think we should think seriously about how to change the balance of power in AI so that AI is knowledge-centered and not just data-centered. Thank you.
I think that is a brilliant summary of where we are. And what I would add to that is the comment that I think you made about evaluation being hard. This comes up because the experience I have in dealing with a network that has scientists and AI researchers is it's possible to teach scientists something about AI, something that they can make quite significant contributions and use it sensibly. We find it harder to teach computer scientists about the science. And it's quite hard if you don't have that scientific background to understand what you've achieved when it comes to actually developing something really important. And therefore, evaluating it when you don't understand the domain you're evaluating in is very difficult. So I think, Gary, you are a really interesting example here of that person who's traveled these domains. And the fact that that's possible and that we are educating people to be researchers in a scientific domain and a computer science, computer engineering, and mathematical domain, these are skills. These are the people that we need to develop. Because without that, I don't think we can take your vision. I absolutely agree with the moral decision we need to make. And having made that, we've got to invest in the people who can do it. And that means that changing some of the training. And that isn't easy. But on the other hand, the techniques, very techniques we're talking about, help with that in the training as well. So I think
training,
it's really,
allocation of money. It has to go from top to bottom.
You need the money, but then you need the people willing to take the money and use it in this way. I think you need both. But
it's incentive systems for interdisciplinary work. Sorry, when I said top to bottom, I didn't mean it starts with the money and flows from there. I mean, it's the whole system is not really set up to do what we need to do.
No, and I think we know we can change it because we have changed. When I started my scientific career, interdisciplinarity was a real nightmare for anybody. Systems have changed to recognize this and reward it. Research councils, funding agencies often actually were leading this against institutional operations. It can be done, is the lesson, but there has to be the will. And I think that's really important. So at this point, I will hand over to Alistair because talking about teaching, I actually have to go and teach and have to teach my class about some environmental chemistry, very hot topic at the moment. And so it's really been enjoyable moderating this session. I think it's been really exciting as a final session of a really exciting week. So I will pass over to Alistair, who for some slightly late concluding remarks, I think.
Thank you very much, Jeremy. You did a wonderful job, and thank you for being with us earlier in the week as well. Really honored to have you here.
Thank you for the opportunity.
I will just make 3 or 4 minutes to close, but before that, I'd like, I'm an economist, I'm not a data scientist, but I'd like to ask one question, if I may. And it goes back to the issue of knowledge, because this was, and the absolutely critical policy point that Gary has raised, because we in the OECD, our job is all about giving policy advice to governments, trying to find best practice, and in dealing with policymakers in the science systems, these are the kind of points that we want to highlight in the forthcoming publication around this. So I would like maybe to revert to some of you, because on this point of R&D priorities to advance this field, which are likely to be underinvested in by the corporate sector. So where should the value added of public sponsorship of R&D really focus on? Because when you look at the national AI strategies, there's very little explicit articulation of this question. Normally, the statements along the lines of, it's essential that AI contribute to those domains which are relevant to the typical supply of public goods and issues around health, mobility in particular, some aspects of utilities and infrastructure. So I would like maybe to come back to you. I've asked 1 or 2 of the speakers earlier on if they could hone in on this question of the R&D priorities, which Gary has just alluded to, and maybe please indulge my lack of expertise here when I get back and ask you a couple of questions there. But in just following up on that point then about better understanding knowledge, is because this is something which came up time and again, it's something that Ken Forbes focused on earlier in the week when we were talking about language-based discovery, and various speakers pointed to the importance of having knowledge, annotated knowledge bases of scientific truth claims. And then I think Eirini's work also pointed to how we might arrive at those kind of knowledge repositories in efficient ways drawing on collective intelligence. But my question here really is, as a layperson trying to understand better the issue of sort of orchestrating, managing knowledge, is the challenge of developing common sense in AI, is that the same challenge as imbuing, let's say, AI scientists? Is that the same challenge as imbuing AI scientists with a common understanding of scientific knowledge? So is developing common sense, is that overarching challenge the same one as getting our AI scientists to understand what we already know about the world of science?
Bart and I both would like to answer. You want to call on one?
Yeah, but please go ahead. Maybe Gary first.
They're related problems. So the core problem is, how do you use knowledge at all? And then there are partly overlapping sets of knowledge that you want to apply. So it's hard to do science without common sense, but it depends on what the nature of your science is. And, some of it's pretty removed from everyday things, whereas, sometimes you might want to have everyday knowledge about cooking, for example, might be helpful when you're doing your chemistry. So they're both critical problems going forward. How do you have expert knowledge and how do you have lay knowledge? And sometimes the expert knowledge is already reified, and if we only had the right tools, we could just throw it all in there, but we don't quite know how to do it yet. And sometimes in the common sense case, like, everybody knows it, but we don't know how to get it down on paper or in machine interpretable form. But they all boil down to, how do we combine this kind of state-of-the-art technology for learning with the need to have abstract knowledge? So they're both manifestations of the same.
If I can add to it, Gary puts it very well. They're very related notions, and common sense knowledge is a form of knowledge that's sort of, I would almost call it pre-scientific. So that's the knowledge that we had before we started doing science. And scientific knowledge is a specialized form of knowledge that works very well for scientific theories. But I think, again, I like the fact that you want to think about this notion of knowledge, and to me it's related to semantics. But policymakers don't understand the issue very well, and actually sort of miss that large gap. And I think our AI researchers, there's also a risk with any scientific discipline. We've become so excited about the progress we've made with deep learning and big data. We're of course not going to highlight what we can't do yet. So I think the community state is a little bit overselling the capabilities that we currently have. I'd like to give one example is let's say you're working on a self-driving car and you train a vision system. The car has to be able to cross a busy crossroad, a main road, and it's waiting at the intersection. So you train a vision system to spot, is there any oncoming traffic? Should I wait or not? We can do that very well. We can probably get superhuman level vision system to detect oncoming traffic. But what the system that you develop that way, what it will miss is that if your car happens to stand next to a truck or something that's blocking the view of your camera, well, no human would say, okay, the road is free because I don't see anything, let's go. But your self-driving, your trained deep learning system will say, I don't see anything oncoming, just go ahead. So it lacks common sense. It lacks an understanding of what's going on. And if your view is blocked, a human is not gonna say, just go ahead. So what I try to stress is that the things we can train with deep learning are very remarkable, but they can miss very obvious things that are very obvious to us. And I think even in terms of scientific discovery and AI for science, I think scientists also have a lot of that knowledge that they use in discovering new concepts and new hypotheses that AI system can't do yet, because we don't have, the AI system don't have the same level of understanding that we have. So I really would like that policymakers are more aware of this gap. I call it AI 3.0. That doesn't exist yet. We have AI 2.0, and there's a lot of work to be done. And deep learning and data may very well be part of what gets us there, but we're not there.
Thank you very much, Bart. I'll go to Hiroaki, and then maybe this will be the last comment of the day, and I'll just make a couple of concluding remarks. Thank you, Hiroaki.
Yeah, I mean, the interesting issue that the the relationship with scientific discovery and common sense. But I think like trying to create an AI with a common sense in order to get the AI scientists is not really the great idea for me. I mean, in a way, like kind of like knowledge we require for the scientific discovery. Some of the, we may not really need to have like everything like beyond like what is relevant. Like scientific AI scientist doesn't really have to be able to play a perfect football game or like a baseball, right? I mean, in a way. And then you ask like grab the top level scientists and see how much of they have a common sense as well. I mean, joking aside. But at the same time, like I think like if you get the AI system, which or like any engineering system which does work, I mean it's more like specific functions. Okay, so you want to have like a mobile phone. It's like a basically communication device. I mean, it's a little bit broader, but like only successful commercial robotic system is like cleaning robot, like a Roomba or things like that. Simply because it's like single functions, function that really require, and but like any attempt to do like general robotics at home didn't work. I mean, so I think we should start from like something like a contextually thing. I mean, that is like a kind of a relatively simple functionality, but like get the superhuman capabilities or any capability that the human cannot do, and then like make it more flexible. Like I should be able to run like a multiple task, which is contextually thick, but like it's probably not aiming at like a level that the human can do. I mean, now of course, like in terms of the commercial investment returns, if you try to create like AI system that mimic a human level general capabilities, I mean, you better hire a human. That would be much cheaper. So I think like we should have like a very practical trade-off in terms of the capabilities and then the contextual thickness of the machinery. And so obviously I think that would be the practical concerns. But at the same time, from the public funded program, I fully agree with what Gary said. Is like right now everyone a lot of AI, particularly deep learning, has been used for like a face recognition. Face recognition became an issue now, so like people putting down. But of course, like advertisement, like or like a specific task that actually will maximize the functionality or maximize the profit of the big corporations. And then try to avoid the harder problem. Like an origin presentation or like hypothesis generations or natural language understanding on the true sense. And of course, like for the corporate side, makes sense to actually to apply the AI system to the low-hanging fruits. We got the deep learning, we got like a GAN, and we got the reinforcement learning, which is much better than before. And then you want to apply to something that has like a convincing result. And that makes sense. But at the same time, if we have to actually, try to budgetize like public funded program, I think it would be very important to actually challenge for the harder task. Harder task is actually something not necessarily accomplished by the straightforward adaptation for the deep learning. Probably requires integration with the symbolic processing and maybe other method as well. And that's where the role of the public funded program. And I think I agree with Gary. I firmly believe single most important mission for the AI is scientific discovery. That will change our civilization. That will save us. So I think like as a public program, I say the same thing for the Japanese government and other government as well. If you had to pick one task for the AI and put money, that would be the scientific discovery. That I'm pretty confident on that.
Thank you, Hiroaki. That's a wonderful way to finish the substantive presentations. And I think this can be a message that we try and put front and center as we deal with as we elaborate the outputs from this work with the OECD, this workshop, and the various short essays which all of the speakers over the last 5 days have been preparing, and including some of those who are not present here. I'd just like to just say a couple of words. Firstly, to say thank you to a few people who helped seed this whole exercise with ideas from over a year ago. Ross King, Hector Zenil, I think Ross has left. Aishik Ghosh from USC Irvine and from CERN, Hugh Cartwright, Justine Cassell, and my former director, actually here, my boss, Dominique Guillec. I'd also like to thank very much the technical team, Sila Valiani, Sylvain Scola, and my colleagues Beatrice and Florence. So with respect to there'll be a publication that will come out in the middle of next year, as I say, comprised of these multiple short essays. And we've tried to go for a rather different approach from a standard OECD book, in as much as all of the speakers have spoken to fairly niche topics. There have been some exceptions, but many of them in the areas of specialization that they're most expert on. And we've asked these to prepare short essays of between even 1 to 6 pages, and to be written in a style which is both rigorous, but also amenable to a non-technical audience, to an intelligent policy analyst, for example, ultimately somebody advising ministers. And I will be working on a synthesis of all of these essays, amongst other things. And once that synthesis is put together, it would be hugely valuable to be able to circulate it amongst many of the people in this community here, because obviously the collective intelligence, the collective expertise is orders of magnitude greater than this team at the OECD possesses. Once the book is ready, it will be disseminated very widely using all of the dissemination mechanisms that the OECD possesses, which are really very considerable, and we'll have short synthetic policy briefs for ministers and for their analysts, which we will put in before governments, both amongst the OECD member countries and the 70 associated non-member countries. Let me then just also close by saying that the whole 5 days has been an intellectual feast. This final session has just been like brain candy, as my director calls it. And I really wish that we were there to have coffee or to have dinner and to exchange in person. And I hope that once the clouds pass over this virus, etc., that at some point we can repeat an event like this. And there has been, I should say, without being self-congratulatory, there's been tremendous positive feedback from these last 5 days, including some people who've got back to us with potentials of funding a future comparable event, maybe 2 years down the road. And in that case, it would be lovely to have you here in Paris, visit OECD headquarters and enjoy this beautiful city here. So with that, I was going to invite the president of Fondation Ipsen, that's the sponsor of this event, just to say a few remarks, but I don't see that he's online. So I'd just like to say thank you very much for all of you are so eminent. Your time is extremely valuable. And it's really a pleasure to be in this context with you. Thank you indeed.